Right now, 19 million miles above the Martian surface, something is passing by that shouldn't exist. Not here. Not moving at 210,000 kilometers per hour. Not outgassing like a comet while barely being pushed by its own jets. 3I Atlas, the third confirmed visitor from another star system, is making its closest approach to Mars tonight, and every spacecraft we have up there is watching. There's a 60-40 split among those brave enough to guess. 60% say it's natural, 40% won't rule out that it was built. The chemistry is wrong, belching carbon dioxide at 8 times the rate of water, a ratio so bizarre it sits 6 standard deviations outside normal. The size doesn't add up, with estimates ranging from 300 metres to 5 kilometres. And the statistics? Well, finding an object this massive as only our third interstellar detection makes some people very uncomfortable. 3 hypotheses, 1 passing visitor. Tonight's data could settle this, or it could make everything stranger. What are Mars orbiters seeing right now as this thing blazes past? What will Hubble catch at perihelion in 3 weeks? And if the numbers still don't add up after tonight, what does that mean for what we think we know about the cosmos? Before we dive into what's actually happening up there, hit subscribe and tell me in the comments where you're watching from tonight. I'd also love to hear your thoughts. Do you think we're alone in observing this, or is there someone else out there watching? Part 1. The flyby that will shock the world. Tonight, October the 3rd, 2025. Right now, as you're hearing these words, something ancient and foreign is screaming past Mars at over 210,000 kilometers per hour. Its name is 3I Atlas, and it's about to get closer to the red planet than most of us will ever get to understanding what it actually is. Multiple spacecraft orbiting Mars have their instruments trained on this visitor, and for good reason. This isn't just another comet. This is the third confirmed interstellar object to pass through our solar system in recorded history, and it's behaving in ways that make astronomers deeply uncomfortable. Let me set the table. In 2017, something called Oumuamua zipped through our neighbourhood and left everyone scratching their heads. It accelerated in ways comets aren't supposed to, looked like a cigar or a pancake depending on who you asked, and vanished before we could get a proper look. Then came 2I Borisov in 2019, which was refreshingly normal. A comet that looked like a comet, acted like a comet, had a nice visible coma of gas and dust and didn't keep anyone up at night. We breathed a collective sigh of relief. The universe made sense again. Then July 1st, 2025 happened. The Atlas survey, which is basically humanity's early warning system for things that might kill us or just really confuse us, spotted something new. Something moving wrong. Not wrong like broken, but wrong like it doesn't belong here. The orbit was hyperbolic, meaning it's not gravitationally bound to our sun. It came from somewhere else, out there in the galactic dark, and it's just passing through. We named it 3I Atlas, the I standing for interstellar, because apparently we've reached the point in human history where we need a naming convention for visitors from other star systems. Now here's where it gets interesting. Hubble Space Telescope observations put an upper size limit on this thing's nucleus, at around 5.6 kilometers across. That's already substantial. For context, that's roughly the size of the asteroid that wiped out the dinosaurs. But here's the catch. It could be much, much smaller. The estimates range down to maybe just 320 to 440 metres. That's a massive error bar, and the reason is simple. We can't see the nucleus directly. It's shrouded in a coma, a cloud of gas and dust that's making it appear larger than it actually is. So we're flying somewhat blind, which is never ideal when you're trying to figure out if something is natural or not. But size isn't the only puzzle. There's this thing called non-gravitational acceleration. When comets heat up near the sun, they release gases, and those gases push the comet around like tiny rocket thrusters. It's subtle, but it's measurable. Oumuamua had this acceleration, and it was weird because we couldn't see any coma to explain it. That's partly why some people started wondering if it might be artificial. 3I Atlas, on the other hand, has a very clear, very active coma. JWST, the James Webb Space Telescope, has seen it outgassing like crazy, and yet the non-gravitational acceleration is incredibly weak, almost negligible. The dynamics suggest something with a minimum mass of about 33 billion tons and a diameter of at least 5 kilometers, if we trust the outgassing numbers JWST is giving us. That's heavy. That's really heavy for something that might be under 6 kilometres across. The math isn't adding up neatly, and when the math doesn't add up in astronomy, that's when people start proposing alternatives. Tonight, 3i Atlas is passing about 18 to 19 million miles from Mars. That's roughly 29 to 30 million kilometres if you prefer metric. In December, it'll make its closest approach to Earth at around 269 million kilometres. So to be absolutely clear, there is zero threat to our planet. None. But this Mars encounter is critical because it's our best chance to study this thing up close. Mars has multiple spacecraft with sophisticated instruments in orbit right now, and they're all watching. This is essentially a cosmic drive-by, and we've got front row seats. The chemistry alone is enough to make you pause. JWST detected a carbon dioxide-dominated coma with a CO2 to H2O ratio of about 8 to 1. That's among the highest ever measured for any comet, anywhere. Most comets are water-rich. Water ice is the dominant volatile. But this thing, it's belching out carbon dioxide like it's trying to terraform Mars in reverse. Along with the CO2, they found water, carbon monoxide, carbonyl sulfide, and water ice particles. But the ratios are all wrong. It's like finding a bird that quacks, has feathers, waddles like a duck, but tastes like beef. Technically possible, but you'd want to double-check your taxonomy. And then there's Avi Loeb. For those unfamiliar, Loeb is a Harvard astrophysicist who's made a second career out of not dismissing the possibility that some of these interstellar objects might be artificial. He proposed a light sail explanation for Oumuamua's acceleration, and while most of his colleagues remain unconvinced, he's now turned his attention to 3i Atlas. He's even created something called the Loeb scale, a 0 to 10 ranking system for how likely an object is to be extraterrestrial technology. 0 means definitely natural, 10 means confirmed alien, and possibly dangerous. In early August, some commentary attributed a rating of 6 out of 10 to 3i Atlas. That's a 60% confidence level that this thing might be technological. Later, in his own Medium post as more data came in, Loeb adjusted it down to 4 out of 10, still elevated, still not dismissing the possibility. And that number, whether you agree with the framework or not, has ignited a firestorm of debate. So we're left with 3 competing narratives as the Mars spacecraft track this object through their sensors tonight. First, the orthodox view, it's a comet. A weird comet, an exotic comet with unusual chemistry, but ultimately just a natural refugee from another star system. Second, the artifact hypothesis. It's something built, something sent, something that might be watching us right now as we watch it. And third, a scenario that somehow manages to be both less fantastical and more terrifying. It's a fragment. A shard from something that was destroyed far away, billions of kilometres from any star, and it's part of a debris stream that we're only just beginning to encounter. If the coma we're seeing is real outgassing, why is the push from that gas so weak? Why is the chemistry so skewed? Why now? Why 3 objects in 8 years when we've been looking at the sky for centuries? Tonight, as 3i Atlas passes Mars, we might start getting answers, or we might just get better questions. Part 2, Data from Mars, the silent witnesses. Let's talk about what's actually happening up there right now. The European Space Agency has 2 spacecraft in Mars orbit that are perfectly positioned for this encounter. Mars Express, which has been studying the red planet since 2003, and the ExoMars Trace Gas Orbiter, a newer addition launched in 2016. Both are slated to monitor 3i Atlas from October 1st through October 7th, with the closest geometry occurring today, October 3rd. And this isn't just a lucky coincidence. Mars orbit is an absolutely killer vantage point for this observation, and here's why. When you're trying to observe something moving at interstellar velocities, every angle matters. From Earth, we're looking at 3i Atlas from one perspective. From Mars, which is currently about 225 million kilometres away from us, depending on where both planets are in their orbits, we get a completely different viewing angle. It's like the difference between seeing a car drive past you on the street versus watching it from a drone overhead. The geometry reveals things that a single viewpoint simply can't. Coma shape, jet directionality, rotational characteristics, all of these become clearer when you have multiple observation points spread across millions of kilometres of space. So what exactly are these Mars orbiters trying to measure? Let's break it down in terms that don't require a PhD. First, spectra. That's the breakdown of light into its component wavelengths, which tells us what gases are present in the coma. Different molecules absorb and emit light at specific wavelengths, so by looking at the spectrum we can identify what's outgassing from the nucleus. JWST already did this in infrared, finding that bizarre carbon dioxide dominance. The Mars instruments will be checking if that signature holds steady or if it's evolving as the object moves through different heating regimes. Second, reflectivity, or albedo. This tells us what percentage of sunlight the object reflects versus absorbs. A very dark object might be carbonaceous, rich in organic compounds, like a burnt marshmallow floating through space. A brighter object might be icy, more pristine. The albedo can give us clues about surface composition and whether there's been radiation processing of the surface materials over millions of years in interstellar space. Third, rotational flicker. If the object is tumbling or spinning, its brightness will change periodically as different faces point toward us. The pattern of that flicker, the light curve, can tell us about the shape. Is it spherical, elongated, irregular, and more importantly, is it rotating in a simple, predictable way, or is it tumbling chaotically like something that's been through trauma? Fourth, coma shape. Gas doesn't just puff off a comet uniformly in all directions. There are jets, focused streams of material that erupt from specific locations on the surface where the ice is most exposed or where subsurface pressure builds up. JWST already reported that the coma is asymmetrically shaped. The Mars orbiters can track how that asymmetry evolves as the solar heating angle changes. If the jets are natural, they should respond predictably to sunlight. If they're not responding as expected, well, that opens doors. And fifth, jetting behaviour. Comets can have outbursts, sudden increases in activity that happen when a pocket of trapped volatile suddenly breaches the surface. These can be triggered by thermal stress, rotational forces, or impacts from smaller particles. Monitoring for outbursts, or the lack thereof, gives us insight into the internal structure. But here's the gotcha. Even at closest approach tonight, 3i Atlas is still incredibly far away from Mars by observational standards. We're talking tens of millions of kilometres. The object itself might be only a few kilometres across, possibly smaller, and it's surrounded by a diffuse coma. It's faint, it's fast, and the Mars orbiters have limited pointing time because they're primarily designed to study Mars, not passing interstellar visitors. So if the orbiters don't see something, that doesn't necessarily mean nothing is there. It might just mean the signal is too weak or the timing didn't line up. This is why combining perspectives is so critical. Hubble gives us resolution. It can separate the nucleus from the inner coma better than almost anything else we have. JWST gives us chemistry. Its infrared instruments are exquisitely sensitive to the molecular fingerprints of gases. The Mars orbiters give us geometry changes over short timescales. Put all three together, and you start constraining the models. A model that fits Hubble's size limits but contradicts JWST's chemistry can be thrown out. A model that explains JWST's carbon dioxide ratio but predicts a coma shape, different from what Mars Express sees? Also questionable. Science works by triangulation, and we're setting up a pretty good triangle here. Now, what would anomalies actually look like in this data? Imagine an unexpected flicker pattern, something that doesn't match a simple rotation. That could suggest a complex, irregular shape, which might be natural but would definitely be interesting. Or an off-axis jet, one that's firing in a direction that doesn't make sense given the solar heating geometry. That could indicate subsurface structure or, if you're feeling speculative, intentional manoeuvring. Or time-variable brightness that's independent of the solar angle. Natural brightness changes follow the sun. If something is getting brighter or dimmer for reasons unrelated to how much sunlight it's receiving, that's harder to explain. There's also been some chatter about whether NASA's Mars Reconnaissance Orbiter might attempt imaging with its HiRISE camera, which is absurdly high resolution by planetary science standards. But I want to be careful here. As of now, there's no official confirmation that HiRISE will be tasked with this observation. It's possible. It's even plausible given the scientific value, but I can't claim it's happening unless an agency confirms it, so file that under watch this space. Looking further ahead, there's another player in this game that most people aren't talking about yet, ESA's JUICE mission. JUICE launched in 2023 and is currently on its way to Jupiter, where it'll study the icy moons. But right now, it's in an interesting position geometrically. Later in 3i Atlas's trajectory, JUICE could potentially offer another long baseline observation from a completely different part of the solar system. That kind of multi-point observation, spread over weeks or months, is how you really nail down an orbit and detect subtle changes. But let's manage expectations. First public images or spectra from tonight's Mars pass might not arrive for days or even weeks. There's a whole pipeline. Raw data comes down from the spacecraft. It gets calibrated to remove instrumental artifacts. It gets processed to enhance signal to noise. Teams write it up. Peer review happens, or at least internal validation. Then, maybe it goes to press or gets posted as a preprint. This is normal. This is how science works. It's not sinister. It's just methodical. So if you're expecting a press conference tomorrow morning with smoking gun evidence one way or another, temper that hope. What we can expect eventually is a much clearer picture of what 3i Atlas is doing at this critical moment in its trajectory. And that picture will feed directly into the next big question. What is this thing actually made of? Part 3. Anatomy of 3i Atlas. Let's get into the physical reality of this object as best we understand it, which I'll warn you up front is not very well. The size envelope is frustratingly wide. Hubble observations put the nucleus upper limit at approximately 5.6 kilometers across. But because the coma is so active and bright, the actual nucleus could be significantly smaller. Some estimates go as low as 320 to 440 meters. That's a factor of 10 uncertainty in diameter, which translates to a factor of 1,000 uncertainty in volume. If this were a murder investigation, we'd be saying the suspect is somewhere between 5'2" and 6'8". Not exactly a tight description. The reason for this uncertainty is straightforward. We're not seeing the nucleus directly. We're seeing sunlight scattering off gas and dust particles in the coma, and the nucleus is hiding somewhere in the middle of that glow. It's like trying to see a pebble at the bottom of a turbulent, muddy river. You know it's there because physics says it has to be, but you can't measure it directly. Now, here's where things get genuinely peculiar. There's a recent dynamics paper that analyses the object's trajectory with exquisite precision, using astrometry from observatories all over the world. Amateur astronomers, professional facilities, everyone contributed position measurements. When you track something over months and fit an orbit to all those data points, you can detect incredibly subtle deviations from a pure gravitational path. Those deviations, the non-gravitational accelerations, tell you how much push the outgassing is providing. For 3i Atlas, that acceleration is about 3 times 10 to the negative 10th astronomical units per day squared. That's a genuinely tiny number. For comparison, many active comets show non-gravitational accelerations orders of magnitude larger. But here's the puzzle. If you know the acceleration and you know the outgassing rate from JWST's observations, you can back-calculate the minimum mass. And the numbers say this thing has to be at least 33 billion tons. Assuming a reasonable density for cometary material, somewhere around 500 kilograms per cubic meter, that implies a diameter of at least 5 kilometers. Notice anything? That's right at the upper end of Hubble's size constraint, so either this thing is genuinely large and massive, or the assumptions going into the mass estimate are wrong. Maybe the outgassing isn't as symmetric as the models assume. Maybe there's something about the compositional structure that makes the acceleration weirdly inefficient. Or maybe, and this is the uncomfortable maybe, it's not a comet at all. Let's talk chemistry, because that's where 3i Atlas really stands out. JWST's NER-spec instrument observed the coma on August 6, 2025, and found a carbon dioxide to water ratio of about 8:1. To put that in context, most solar system comets observed at similar distances from the Sun show water as the dominant volatile, often by a large margin. A typical ratio might be closer to 1 part CO2 to 10 or 20 parts water. 3i Atlas has flipped that on its head. It's producing 8 times more carbon dioxide than water. Along with the CO2 and H2O, they also detected carbon monoxide, carbonyl sulfide, and water ice grains. The whole cocktail is there. But the proportions are bizarre. What could cause this? One possibility is formation environment. In a protoplanetary disk, the temperature drops as you move away from the star, and different ices condense out at different distances. Water ice forms relatively close in. Carbon dioxide and carbon monoxide ices form further out, where it's colder. If 3i Atlas formed near what's called the CO2 ice line in its birth system, it might naturally be enriched in carbon dioxide relative to water. That's a reasonable, natural explanation. Another possibility is radiation processing. Imagine this object has been drifting through interstellar space for millions of years. bombarded by cosmic rays and ultraviolet light from distant stars. That radiation can alter surface chemistry, breaking molecular bonds and creating new compounds. It can also create an insulating crust that traps more volatile materials underneath. If the crust preferentially seals in water ice, but allows carbon dioxide to escape more easily, you'd get exactly the kind of skewed outgassing ratio we're seeing. Again, natural, but exotic. The trajectory itself is unambiguous. This is a hyperbolic orbit, meaning the object is moving faster than escape velocity for the solar system. There's no bound path. It came from interstellar space, it's swinging past the sun, and it's heading back out into the dark. Perihelion, the closest point to the sun, happens around October 30th, 2025, at a distance of about 1.4 astronomical units. That's just outside Earth's orbit, closer to the sun than Mars, but further than Venus. At perihelion, solar heating will be at its maximum, so if there's going to be any dramatic change in activity or any weird behaviour, that's when we'd expect to see it. The speed is worth emphasising again. 210,000 kilometres per hour, or about 130,000 miles per hour. That's roughly 58 kilometres per second. For context, Voyager 1, the fastest human-made object currently leaving the solar system, is moving at about 17 kilometres per second relative to the Sun. 3i Atlas is more than 3 times faster. That velocity is a combination of its initial interstellar drift speed plus gravitational acceleration as it fell toward the Sun. And it's that speed, combined with the orbital inclination, that proves beyond any doubt that this thing didn't originate here. Now let's compare this to baseline comet behaviour. Most comets in our solar system, even the long-period ones coming from the Oort cloud, show stronger water dominance when they're active. The carbon dioxide to water ratio typically increases only at very large distances from the Sun, where water ice is too cold to sublimate efficiently, but CO2, which is more volatile, can still outgas. But 3i Atlas is active relatively close to the Sun and still maintaining that weird ratio. It's sitting way off the normal trend, about 6 standard deviations above typical values. In statistics, 6 sigma is where you start questioning whether your measurement is even from the same population. It's an outlier among outliers. And then there's the acceleration paradox. Outgassing should push the comet around. JWST sees plenty of outgassing, but the actual measured push is tiny. How do you reconcile that? One explanation is balanced jets. If the nucleus is venting material from multiple locations and those jets roughly cancel each other out in terms of net force, you'd see lots of activity but minimal acceleration. It's like having 4 rocket thrusters firing in a square pattern, all with equal strength. The object would shake, but it wouldn't move. That's plausible. That's actually fairly common for some comets. But it requires a specific geometry and symmetry that we haven't confirmed yet. The alternative reading is that the object is just really massive, and the gas production, while visually impressive, isn't enough to significantly alter its trajectory. Think of trying to push a boulder with a leaf blower. Lots of air moving, minimal effect on the rock. If 3i Atlas is legitimately 5 kilometres across with a solid interior, the outgassing might simply be too weak to measurably accelerate it. That works mathematically. But it also means this thing is a beast, and finding a 5-kilometre interstellar object so early in our survey history would be, statistically speaking, weird. We'll get into why that's weird when we talk about the mothership hypothesis. So where does this leave us anatomically? We've got something between 300 metres and 5.6 kilometres across. It's surrounded by an active, asymmetric coma rich in carbon dioxide. It's moving on a clear interstellar trajectory at absurd speed. Its outgassing chemistry is off the charts abnormal, and despite all that activity, it's barely being pushed around by its own jets. Every measurement we take seems to add a new layer of strangeness instead of clarifying the picture. And that strangeness is exactly what makes some people wonder if we're measuring the wrong thing entirely. Part 4. The Loeb Scale and the 60% Verdict. Alright, let's address the elephant in the telescope. Avi Loeb, chair of Harvard's astronomy department, former chair of the Board on Physics and Astronomy of the National Academies, has proposed a framework for quantifying how likely an interstellar object might be artificial. He calls it the Loeb Scale, and it runs from 0 to 10. 0 means definitively natural, a rock or a comet with no possibility of technological origin. 10 means confirmed extraterrestrial technology, and potentially dangerous. It's deliberately modelled after scales we already use for other existential risks, like the Torino scale for asteroid impacts or the Richter scale for earthquakes. The idea is to give researchers, media and the public a common language for discussing something that's historically been either dismissed outright or sensationalised beyond recognition. In early August 2025, some public commentary attributed a rating of 6 out of 10 to 3i Atlas under this framework. That's a 60% confidence level that this object might be technological in origin. Later, in his own Medium posts as more data accumulated, particularly the JWST chemistry results, Loeb revised that rating down to 4 out of 10, or 40%. That's still elevated. That's still saying there's a non-trivial chance this isn't just a space rock, and predictably, that claim has set off a debate that split the astronomy community down the middle. So what pushes the score up? Let's walk through Loeb's reasoning, which, whether you agree with it or not, is methodical. First, size rarity. If 3i Atlas is genuinely 5 kilometers or larger, as the dynamics and mass estimates suggest, that's unusual. Most objects we detect drifting through interstellar space should be small, because small objects are exponentially more numerous than large ones. Finding a dinosaur killer-sized chunk so early in our survey history, when we've only confirmed 2 previous interstellar visitors, strikes Loeb as statistically improbable. It's like winning the lottery on your 3rd ticket. Possible, sure, but suspicious. Second, the weak non-gravitational acceleration despite obvious activity. If you're outgassing enough material to create a visible coma that shows up in JWST spectra, you should be getting pushed around. The fact that the push is so minimal despite the activity suggests either an unusually massive object or a thrust profile that's somehow compensating. Loeb notes that both scenarios are possible naturally, but they're also consistent with a large solid artifact that's venting something for reasons unrelated to thermal sublimation. Third, the chemistry. That 8-to-1 carbon dioxide to water ratio is genuinely odd. While there are natural explanations, as we've discussed, it's also true that if you were designing a propulsion system for an interstellar probe, you might prioritise volatiles based on efficiency and storage rather than what's cosmically abundant. Carbon dioxide sublimates at higher temperatures than water ice, so it might be easier to store and control over millions of years in space. This is speculative, obviously, but it's the kind of detail that makes Loeb's antenna twitch. Now, what pushes the score down? First and foremost, the coma itself. JWST sees clear spectral signatures of natural volatiles: water, carbon dioxide, carbon monoxide, carbonyl sulfide, and water ice. Grains. This is chemistry you'd expect from a comet. There's no hint of industrial compounds, no unusual isotopic ratios that might suggest artificial synthesis, no narrow band emissions that could be leakage from electronics. The object is outgassing in a way that's consistent with solar heating and sublimation. That's a strong point in favour of the natural hypothesis. Second, no clear manoeuvres. If this were a functioning spacecraft, you'd expect to see deliberate course corrections, acceleration or deceleration that's inconsistent with gravitational forces and outgassing. So far, 3i Atlas's trajectory is entirely consistent with a ballistic path. Gravity plus minimal rocket effect from the coma. There's no evidence of active control. Third, the arrival geometry isn't particularly suspicious. Some people have speculated that if an alien probe wanted to study the solar system, it might come in at an unusual angle to avoid detection or to maximise observation time. 3i Atlas's orbit is inclined, but that's normal for interstellar objects. They're not on the ecliptic plane because they didn't form in our solar system. The angle isn't screaming stealth approach or deliberate survey pattern. It looks, for lack of a better term, random. So where does mainstream astronomy stand? NASA's public-facing pages and press releases call it an interstellar comet. There's no threat to Earth. The language is cautious but clear. This is being treated as a natural object unless something drastically changes. The European Space Agency echoes that stance. Most professional astronomers I've seen comment publicly are in the comet camp, emphasising that while the chemistry is unusual, unusual is not the same as impossible, and we've only looked at a handful of interstellar objects. Our sample size is 3. Drawing sweeping conclusions from 3 data points is like trying to determine the average height of humans by measuring 3 random people. You might get lucky, but you're probably going to be wrong. But here's where the media crosscurrents muddy the waters. Some outlets, particularly those that thrive on clicks and outrage, amplify the alien angle. Headlines scream about motherships and invasion fleets. Other outlets go the opposite direction, mocking anyone who even entertains the possibility as conspiracy theorists or attention seekers. The actual scientific middle ground, which is probably natural but let's keep an eye on it, gets squeezed out because nuance doesn't drive engagement. Now let's talk about fairness. The principle in science is that extraordinary claims require extraordinary evidence. Carl Sagan made that phrase famous, and it's become almost a mantra. If someone claims 3i Atlas is an alien spacecraft, the burden of proof is enormous. What would that evidence look like? Engine-like manoeuvres that can't be explained by outgassing. Narrowband radio emissions at frequencies that don't occur naturally. Optical. Signatures consistent with manufactured surfaces. Specular reflections, panel glints, geometric structures. Thermal emissions that don't match solar heating patterns. Basically, you'd need something that unambiguously screams technology. Loeb's framework is an attempt to quantify that burden. Instead of a binary, natural or alien, it's a sliding scale. The idea is that you can map observed anomalies onto a continuous score, and that score should move as new data comes in. Early on, with limited information, you might assign a higher score because uncertainty is high. As you gather more data, particularly data that fits natural models, the score should drop. And that's exactly what we've seen with 3i Atlas. The initial 6 out of 10 was based on incomplete information. The revised 4 out of 10 incorporates JWST's chemistry and the lack of observed manoeuvres. If future observations show stable, predictable comet-like behaviour through perihelion, the score should drop further. But there's a second axis to consider, and this is where things get philosophically interesting. The scale isn't just natural versus artificial, it's also threat versus benign. You could have an artificial object that's entirely non-threatening, a dead probe, a malfunctioning satellite from a civilization that's long extinct, a passive data collection device that has no interest in us whatsoever. Conversely, you could have a natural object, like a comet on a collision course, that's extremely threatening. The two axes are independent. Loeb's scale tries to capture the artifact probability, but the public discourse often conflates that with danger, which is where dark forest talk starts to ignite, and that's a whole other conversation we'll get into later. The key takeaway here is that Loeb's score is a hypothesis-generating tool, not a verdict. It's a prior, in Bayesian terms. You start with some probability based on available evidence, and you update as new evidence arrives. Most scientists would currently put the prior much, much lower than 4 out of 10. But the framework itself, the idea that we should have a systematic way to evaluate these objects, is actually pretty reasonable. We're going to see more interstellar visitors. The Vera Rubin Observatory, which is about to come online, will detect them at a rate orders of magnitude higher than current surveys. Having a common language for how weird is this one might actually be useful. So is 3i Atlas 60% likely to be alien technology? Almost certainly not. Is it 40%? Still probably not. But is it 0%? That's the question Loeb is asking us to take seriously, and whether you find that question provocative or pointless, it's the question that's keeping this story alive as instruments across the solar system train their gaze on a tiny, distant speck hurtling past Mars tonight. Next, we need to unpack the physics that makes this object undeniably interstellar and where the mathematical cracks start to show. Part 5. The physics puzzle. How do we actually know this thing is interstellar? That's not a trivial question. Space is big, really big, and things move in complex ways under the influence of multiple gravitational fields. You can't just point at something moving fast and declare it's from another star. You need rigorous orbital mechanics, and fortunately, we have that. When you track an object across the sky over weeks or months, you're collecting position data. Each observation gives you a coordinate, right ascension, and declination at a specific time. Feed enough of those observations into orbital mechanics software, and it solves for the 6 parameters that define an ellipse or hyperbola: semi-major axis, eccentricity, inclination, argument of perihelion, longitude of ascending node, and time of perihelion passage. For objects bound to the Sun, the eccentricity is less than 1. The orbit is an ellipse, closed, repeating. For interstellar objects, the eccentricity is greater than 1. The orbit is a hyperbola, open on both ends. The object came from infinity, it's swinging around the Sun, and it's heading back to infinity. 3i Atlas has an eccentricity significantly greater than 1. There's no closed solution. This thing is not, and never was, gravitationally bound to our Sun. The hyperbolic excess velocity, the speed it has relative to the Sun after you subtract out gravitational acceleration, is another smoking gun. For 3i Atlas, that excess velocity is on the order of tens of kilometers per second. That's the speed it was moving through interstellar space before it encountered our solar system. No natural process within the solar system can impart that kind of velocity to an object without a close gravitational assist from a massive body, and the trajectory doesn't pass near any such body in a way that would explain it. The object arrived with that speed. It didn't gain it here. But here's where the uncertainties creep in. We can measure the current orbit with exquisite precision. We can project backward to figure out roughly where the object came from. But roughly is doing a lot of work in that sentence. The errors explode as you go back in time. Over millions of years, tiny uncertainties in the current trajectory compound into enormous positional uncertainties in the past. We can say with confidence that 3i Atlas originated in interstellar space, probably from somewhere in the general direction of the constellation it was moving from when detected, but pinpointing the exact star system. Not happening. The galactic velocity field is complex. Stars move. Objects get perturbed by passing stars. Trace the orbit back 1 million years, and the error cone is dozens of light years wide. Trace it back 10 million years, and it's hundreds. There's also the question of what ejected this thing in the first place. Stars don't just toss multi-kilometre objects into interstellar space for fun. You need a mechanism. Gravitational scattering by giant planets during the formation of a planetary system is one option. Models show that young star systems are chaotic places, with planets migrating, asteroids and comets getting flung around. Some percentage of that material achieves escape velocity and becomes interstellar. In fact, some estimates suggest there might be trillions of rogue comets and asteroids drifting between the stars in our galaxy right now, outnumbering the stars themselves. Another possibility is a close stellar encounter. If two stars pass within a few light years of each other, the gravitational tides can strip comets from their respective Oort clouds and send them flying. Or, in a more dramatic scenario, a star could get ejected from a star cluster, carrying some of its cometary material with it before losing it to interstellar space. Or, and this is the scenario that feeds the debris field hypothesis, something catastrophic happened. A planetary collision. A tidal disruption event where a planet wandered too close to its star and got ripped apart. A supernova shockwave from a nearby stellar explosion. Any of these could shatter a world and send the pieces hurtling outward at high speed. Now, let's talk about what happens at perihelion, which is coming up in just under a month, October 30th, 2025. At that point, 3i Atlas will be at its closest to the Sun, about 1.rem continue edit 4 astronomical units, roughly the distance between the Sun and Mars. Solar heating will be at maximum. If this is a natural comet, we'd expect to see an increase in outgassing activity. The sublimation rate should spike. The coma should brighten, and possibly expand. If the non-gravitational acceleration we've been measuring stays low, or doesn't increase proportionally with the outgassing, that strengthens the heavy nucleus model. It suggests the object is genuinely massive, and the gas production, while dramatic to our instruments, is still insufficient to significantly alter its trajectory. But perihelion could also reveal something stranger. Comets sometimes exhibit outbursts at perihelion, sudden spikes in activity that aren't smoothly correlated with solar heating. These can be caused by subsurface pockets of volatile material suddenly breaching the surface, like a pressure cooker valve releasing. If 3i Atlas has an outburst, and if that outburst happens to produce a measurable change in trajectory, we'd need to carefully model whether that change is consistent with isotropic venting, or if there's directionality that suggests structure. I'm not saying we'd find evidence of manoeuvring. I'm saying we'd need to rule it out with high confidence. The JWST mass loss measurements combined with the dynamics give us that minimum mass estimate of 33 billion tons. But let's be honest about the assumptions baked into that number. It assumes the outgassing JWST measured in early August is representative of the object's average behaviour over the time period used for the orbit fit. If the object is more active at some times and less active at others, the mass estimate changes. It assumes the outgassing is roughly symmetric, or at least that the asymmetries average out over a rotation. If there's a preferred jet direction that's persistently pushing in one orientation, the math changes. It assumes a certain efficiency for how outgassing translates into thrust, which depends on the molecular weight of the gas and the speed at which it's ejected. Carbon dioxide and water have different molecular weights. The mix matters. So the 33 billion tonne figure is a lower limit based on specific modelling choices. It's not a measurement in the same way Hubble's size limit is a measurement. It's an inference, and inferences are only as good as the models they're built on. Then there's the spin and light curve problem. If we could measure how fast this thing is rotating and what the periodicity of its brightness variations looks like, we'd learn a lot about its shape. A perfectly spherical object rotating wouldn't show brightness variations. An elongated object tumbling end over end would brighten and dim as different cross-sections face us. The amplitude of those variations tells you the axis ratio, the period tells you the spin rate, but measuring that requires high-cadence photometry over extended periods, and the coma complicates everything. The brightness we see is dominated by the coma, not the nucleus. So extracting the nucleus rotation signal from the coma noise is extraordinarily difficult. Some future observations might crack this. If the object passes in front of a background star, the occultation could give us a direct size measurement. If someone gets a radar return, which is a long shot given the distance but not impossible, that would give us both size and spin rate. If the object's activity dies down significantly post-perihelion and we can finally see the nucleus directly, Hubble or JWST could nail the dimensions. There's a historical parallel here worth mentioning. Oumuamua, the first interstellar visitor, prompted dozens of papers trying to backtrace its origin. Where did it come from? Which star system ejected it? The best efforts, using Gaia data on stellar positions and motions, identified a few candidate systems, but the uncertainties are massive. Over the millions of years Oumuamua has been travelling. Tiny perturbations from passing stars, radiation pressure, interstellar dust drag, all of these add up. The same problem applies to 3I Atlas. We can say it came from interstellar space in this general direction, but we can't say it came from Tau Ceti, or it was ejected from the Hyades cluster. The resolution just isn't there, and then there's the jet cancellation mechanism, which deserves a plain language explanation because it's central to reconciling the weak acceleration with the strong outgassing. Imagine a comet nucleus shaped like a potato. Multiple patches on the surface are outgassing. If those patches are distributed symmetrically, and if they're all producing roughly equal thrust, the net force on the nucleus could be close to zero. It's like 4 people pushing on a car from 4 different sides with equal strength. The car doesn't move, it just experiences stress. This isn't exotic physics. We've seen it in solar system comets. Comet 67P Churyumov-Gerasimenko, which the Rosetta spacecraft orbited for 2 years, showed exactly this kind of behaviour. Multiple active regions, complex jetting, but relatively modest non-gravitational acceleration because the jet's mostly cancelled, so it's plausible for 3I Atlas. But it does require a specific geometry, and it's worth noting that not all comets exhibit this. Some are dominated by a single large jet, and those do show strong acceleration. The fact that 3I Atlas seems to be in the balanced jets category is just another item on the list of things that are consistent with natural processes, but also slightly unusual. There's also a crowd science angle here that's worth celebrating. The orbital solution for 3I Atlas is built on thousands of position measurements from observatories all over the world, professional facilities like Gemini, Subaru and the European Southern Observatory, but also amateur astronomers with backyard telescopes contributing data to the Minor Planet Center. This is citizen science at scale. Every single observation helps refine the orbit, tighten the error bars and constrain the models. Without that distributed network, we'd have a much fuzzier picture of what this object is doing. So where does Act 1 leave us? The case for weird but natural is strong. The chemistry is odd but explainable. The size and mass are uncertain but not impossible. The trajectory is unambiguously interstellar. The weak acceleration despite strong outgassing is puzzling, but could be balanced jets or high mass. Every anomaly has a plausible natural explanation, but the anomalies keep piling up, and each one, individually resolvable, contributes to a cumulative sense of strangeness. It's like a murder case, where every piece of evidence has an innocent explanation, but when you lay them all out on a table, the pattern starts to look suspicious. The door isn't closed, it's cracked, and light is spilling through. Next, we need to put these three hypotheses head to head and see which one survives contact with the data. Part 6. The Comet Hypothesis. Nature's Exotic Child. Let's start with the simplest explanation, the one that requires the fewest assumptions and fits most comfortably with what we already know about the universe. 3I Atlas is a comet. An interstellar comet, yes. An unusual comet with exotic chemistry, absolutely. But fundamentally it's a dirty snowball, a chunk of ice and rock that formed in a protoplanetary disk around another star, got ejected through gravitational interactions, and has been drifting through the galaxy for millions or billions of years until it happened to pass through our neighbourhood. This is the orthodox view. It's what NASA's public statements emphasise. It's what most professional astronomers default to when asked. And it's not just institutional inertia or a refusal to consider alternatives. It's based on positive evidence. JWST detected water, carbon dioxide, carbon monoxide, carbonyl sulfide, and water ice grains in the coma. This is precisely the cocktail you'd expect from a comet. These are natural volatiles, compounds that form under cold conditions in space and sublimate when heated by starlight. The spectral signatures match laboratory data for these molecules. There's no ambiguity in the identification, but let's address the elephant in the room, that 8:1 carbon dioxide to water ratio, because this is genuinely strange, and it's the detail that keeps this hypothesis from being a slam dunk. In our solar system, we've observed hundreds of comets. Most of them, when active near the Sun, show water as the dominant volatile. The typical CO2 to H2O ratio is much less than 1. You might see 1 molecule of carbon dioxide for every 10 or 20 molecules of water. Comets like C2001A2 or C1995-01 Hale-Bopp, which were extensively studied, fit this pattern. Even comets that are relatively CO2-rich rarely exceed a 1:1 ratio. 3I Atlas is producing 8 molecules of carbon dioxide for every molecule of water. That's not just a little off the trend. That's 6 standard deviations above the mean. In medical diagnostics, that's the difference between slightly elevated cholesterol and call an ambulance. So we need an explanation. The formation environment hypothesis goes like this. In a protoplanetary disk, temperature decreases with distance from the star. Close in, you've got hot, rocky material. Further out, water ice starts to condense. This is called the snow line or frost line, typically a few astronomical units from the star depending on its luminosity. But keep moving outward and you reach colder regions where more volatile ices condense. Carbon dioxide ice forms at slightly lower temperatures than water ice. Carbon monoxide, even more volatile, condenses further out still. If 3I Atlas formed in a region of its birth disk that was just cold enough for abundant CO2 ice, but where water was already depleted or locked into minerals, you'd get a CO2-rich composition naturally. There's precedent for this kind of compositional zoning. In our solar system, Kuiper belt objects show variations in their ice content depending on where they formed. Some are water-rich, others have more methane or nitrogen ice. The distribution isn't uniform. Extrapolate that to another star system with a different stellar mass, a different disk temperature profile, maybe a different metallicity, and you could absolutely get conditions that favour carbon dioxide over water. The radiation processing hypothesis adds another layer. Imagine 3I Atlas has been in interstellar space for 10 million years. During that time, it's been bombarded by cosmic rays, high-energy protons and atomic nuclei accelerated by supernova remnants and other violent events. It's also been bathed in ultraviolet light from distant stars. This radiation penetrates the surface layers and breaks chemical bonds. Water molecules can be split into hydrogen and oxygen. Carbon dioxide can be broken down or converted to other compounds. But the radiation also creates an insulating crust, a layer of processed material that's less volatile than the pristine ice underneath. Here's the key insight. Water ice and carbon dioxide ice have different sublimation curves. Water starts outgassing significantly around 150 to 200 Kelvin. Carbon dioxide sublimates at lower temperatures, around 150 Kelvin and below. If you've got a radiation-processed crust that's providing some insulation, the outer layers might warm up enough to release carbon dioxide while keeping the water locked in deeper layers. You'd see CO2 venting preferentially, even though there's plenty of water inside. The nucleus is essentially a thermos bottle with a leaky cap, and the leak favours the more volatile species. This model explains why the CO2 to H2O ratio might be high now, but it also makes a prediction. As the object gets closer to the Sun and the heating penetrates deeper, water should start to dominate. If we see the ratio shift toward more water activity at perihelion, that supports the radiation crust model. If the ratio stays stubbornly high, that's more consistent with a composition that's intrinsically CO2 rich. Now let's tackle the acceleration paradox with the balanced jet solution. This is actually less exotic than it sounds. Comet nuclei are not smooth spheres. They're irregular, with valleys, craters, cliffs and plains. Some areas are covered in dust that insulates the ice underneath. Other areas have exposed ice or thin dust layers that allow sublimation. When sunlight hits these active regions, gas jets erupt, carrying dust with them. Each jet produces thrust, like a tiny rocket engine. If you've got multiple jets firing from different parts of the nucleus, and if the geometry is such that the thrust vectors roughly cancel, the net acceleration is small, even though the total gas production is large. This isn't just theoretical. Rosetta's observations of Comet 67P showed this in action. The comet had multiple active regions, jets firing from the neck region and the lobes. The net non-gravitational acceleration was present but modest because the jets were distributed. For 3I Atlas, if the asymmetric coma JWST observed is the result of multiple jets from different locations on the nucleus, and if those jets are oriented such that their horizontal components cancel, while the vertical components produce the observed coma shape, you'd get exactly what we're seeing. High activity, dramatic coma, weak net push. The math works, the physics works. It requires a specific geometry, but comet nuclei come in all shapes and sizes. It's not implausible. But here's where we need intellectual honesty. The lower limit mass of 33 billion tons, if we take it at face value, implies a diameter of at least 5 kilometers, assuming typical cometary density. That's big. Most comets we know are smaller. The famous ones, Halley's Comet, is about 15 kilometers long but only about 8 kilometers wide on average. Hale-Bopp was estimated at roughly 60 kilometers, so 5 kilometers is substantial but not unprecedented. However, finding a 5-kilometer interstellar object as only the third confirmed ISO is statistically curious. The selection effect argument goes like this. Our surveys are biased toward detecting bright objects. Brightness depends on both size and activity. A small, very active comet might be easier to spot than a large, inactive asteroid. So maybe we're just seeing the tip of the iceberg, and there are tons of smaller, fainter interstellar objects that we're missing. As surveys improve, particularly when Rubin comes online, we'll start detecting those smaller objects, and the size distribution will normalise. The fact that we found a big one early is just luck, good or bad depending on your perspective. The sceptical counter is that if 5-kilometer ISOs are common enough that we've hit 1 out of 3 detections, the interstellar population must be skewed toward large objects in a way that's hard to explain. Most models of planetary system formation predict that small debris should vastly outnumber large objects. The size-frequency distribution typically follows a power law with a steep slope. Finding large objects first is possible, but it's the less likely outcome, so either our models are wrong, or our sample size is still too small to draw meaningful conclusions, or there's something unusual about the objects we're detecting. That brings us to what Mars and perihelion observations could confirm. If we see jet structure evolving predictably with solar angle, that's strong evidence for a natural comet. If the coma asymmetry shifts in ways that correlate with changing illumination geometry, that's what you'd expect. If the CO2 to H2O ratio starts shifting toward more water as heating intensifies, that supports the radiation crust model. If we detect rotational periods and they're consistent with a tumbling, irregularly shaped nucleus that's also comet-like. Conversely, if the activity stays strangely uniform regardless of solar heating, that's harder to explain naturally. If we see jet behavior that doesn't correlate with sunlight, that raises questions. If the object's brightness or spectral signature changes in ways that aren't thermally driven, that's anomalous. One more critical point. No Earth hazard. The closest 3I Atlas comes to our planet is about 270 million kilometers in December. For context, Mars at its closest approach to Earth is about 55 million kilometers. The Moon is roughly 400,000 kilometers away. 3I Atlas is nowhere near a collision course. Even if it were significantly larger than estimated, even if it fragmented, the pieces would not intersect Earth's orbit. This is important because fear-mongering about doomsday comets or invasion fleets drives clicks but does a disservice to public understanding. The risk is zero, not low, zero, so the comet hypothesis stands on solid ground. Unusual chemistry, check. Weak non-gravitational acceleration, explainable through balanced jets or high mass. Interstellar origin, consistent with ejection mechanisms we understand. Observable coma with natural volatiles confirmed. Size and mass uncertainties, not yet fatal to the model. It's the simplest explanation that fits the data. But simplicity isn't the same as certainty, and there are people, serious scientists with credentials and track records, who argue we should at least consider the possibility that the numbers don't line up because we're measuring the wrong kind of object entirely. Part 7. The Mothership Hypothesis, Artifact Among the Stars. Now we wade into deeper, colder water. The Mothership Hypothesis, or more generally the Artifact Hypothesis, suggests that 3I Atlas might not be a natural comet at all. It might be something built, something sent, an interstellar probe, possibly dead, possibly dormant, possibly still operational, that happens to be passing through our solar system and is doing an excellent job of mimicking a comet. Let's be clear from the start. This is not the mainstream view. This is not what NASA is saying. This is not what most astronomers believe, but it's being discussed, primarily by Avi Loeb and a few colleagues, and the arguments are worth taking seriously even if you ultimately reject them. Science progresses by considering alternatives, not by dismissing them out of hand. The core of the artifact argument rests on statistical rarity and behavioural anomalies. Loeb's position, articulated in various Medium posts and interviews, is that by naive statistics, we should encounter countless small interstellar objects before we find a large one. The size-frequency distribution of natural debris ejected from planetary systems should heavily favour small objects. Pebbles, boulders, maybe small asteroids. But 5-kilometre class objects should be rare. So finding one as only our third confirmed interstellar detection is, in Loeb's view, suspicious. It's like randomly sampling 3 fish from the ocean and catching a whale. Possible, but it makes you wonder if the population is being mischaracterized. Now many astronomers dispute this logic. They point out that detection bias is enormous. We're far more likely to spot large objects because they're brighter. The surveys that found Oumuamua, Borisov and 3I Atlas are sensitivity limited. They're skimming the brightest, most obvious targets. As technology improves, we'll start detecting smaller, fainter ESOs, and the size distribution will likely normalise. The whale isn't rare, it's just the only thing our net is big enough to catch right now. Loeb acknowledges this but argues that even accounting for detection bias, the numbers are tight enough to warrant elevated scrutiny. The second pillar of the argument is the weak non-gravitational acceleration despite clear outgassing. We've already discussed the balanced jets explanation, which is natural and plausible. But Loeb notes that balanced jets require a specific, somewhat contrived geometry. You need multiple active regions with thrust vectors that happen to cancel. That's possible, but it's also a bit of a just-so story. You're fine-tuning the model to fit the data. Alternatively, if the object is not outgassing for thermal reasons but is instead venting something intentionally, perhaps for propulsion or thermal management of internal systems, you might see exactly this profile. Visible coma from expelled material, minimal net acceleration because the venting is controlled or symmetric by design. The third pillar is the trajectory, and here I need to tread carefully because the data doesn't actually support the idea that 3I Atlas's trajectory is anomalous. Its orbit is hyperbolic, consistent with an interstellar origin, but the inclination and approach angle are within the range you'd expect for a randomly arriving object. It's not coming in perpendicular to the ecliptic in a way that screams deliberate survey pattern. It's not decelerating or manoeuvring. As far as we can tell, it's on a purely ballistic path. However, Loeb and others have pointed out that if you were designing a stealth probe, you might intentionally avoid obvious maneuvers that would give away your artificial nature. You'd coast on a trajectory that looks natural. You'd use passive observation rather than active scanning. You'd vent material, if necessary, in ways that mimic comet outgassing. In other words, the absence of obvious technological signatures doesn't prove naturalness. It might just indicate competent engineering. This is an unfalsifiable argument in its strong form, which makes it scientifically frustrating. But it's worth noting that absence of evidence is not evidence of absence, a phrase that cuts both ways in this debate. So what would count as evidence for the artifact hypothesis? This is where the rubber meets the road. First, repeatable manoeuvres. If 3i Atlas changed its trajectory in ways that couldn't be explained by outgassing, that would be a smoking gun. If it accelerated, perpendicular to the sun's direction when it should be decelerating, or if it executed a course correction that aligned it toward a specific target, that would be impossible to explain naturally. Second, specular reflections or panel glints. Natural bodies are rough and irregularly shaped. Manufactured surfaces, especially solar panels or mirrors, produce sharp, bright reflections when sunlight hits them at specific angles. If photometric observations caught a sudden, brief spike in brightness that repeated with a period matching a rotation that would suggest flat reflective surfaces. Third, narrowband transmissions. Comets produce broad-spectrum thermal emission and scattered sunlight. If radio telescopes detected a signal from 3i Atlas at a specific frequency, particularly a frequency that doesn't correspond to any natural molecular line, that would be extraordinary evidence. Fourth, non-thermal emission. If infrared observations showed the object was warmer than solar heating alone could explain, that might indicate internal power generation, though we'd need to rule out subsurface heat from radioactive decay or tidal heating first. So far, none of these have been observed. The trajectory is ballistic. No glints or reflections have been reported beyond what you'd expect from a dusty, icy surface. No radio signals. The thermal profile, to the extent we can measure it, is consistent with solar heating. Loeb's response to this is essentially, keep looking. He argues that the stigma around searching for technosignatures has caused astronomers to underinvest in the kinds of observations that might detect them. If no one is seriously looking for radio signals or unusual manoeuvres, then of course we won't find them. He advocates for more aggressive monitoring, more high-cadence photometry, more multi-wavelength coverage, and to be fair, he's right that if we assume something is natural and don't look for artificial signatures, we'll never find them even if they're there. There's a historical parallel with Oumuamua that's worth revisiting. When Oumuamua exhibited that unexplained acceleration, Loeb and his colleague Shmuel Bialy published a paper suggesting one possible explanation was a light sail, a thin reflective sheet propelled by radiation pressure from the sun. The idea was that if Oumuamua were artificially thin like aluminum foil, it could be accelerated by sunlight in a way that mimicked the observed trajectory. The paper was carefully worded, presenting the light sail as one option among several, not as a definitive claim. The reaction was swift and polarized. Some media outlets ran with "Harvard astronomer says Oumuamua is alien spacecraft" headlines. Other astronomers pushed back hard, arguing that natural explanations like hydrogen outgassing or nitrogen ice sublimation were far more plausible. The debate became heated, sometimes personal. Loeb was accused of attention-seeking. His critics were accused of closed-mindedness. The scientific process became tangled with media narratives and professional politics. What's important to extract from that mess is this. Extraordinary claims do require extraordinary evidence, but that standard shouldn't morph into never consider the possibility. If the prior probability of extraterrestrial artifacts is truly zero, then no amount of evidence will ever be sufficient because you've ruled it out axiomatically. That's not science. That's dogma. A more defensible position is that the prior is very low but non-zero, and it updates with data. Loeb's framework tries to formalize that updating process. Current data reality is that JWST's natural volatiles and the lack of detected maneuvers strongly support the big comet model over the artifact model. The spectral signatures are precisely what you'd expect from ice. The coma shape and evolution are comet-like. The object is behaving in every measurable way like a comet. So Occam's razor points toward comet. But Loeb would argue that Occam's razor is a guideline, not a law, and sometimes the simplest explanation is wrong. Now let's address the media versus science tension. Mainstream teams, NASA, ESA, and most university researchers are cautious about hostile probe framings. Partly this is responsible communication. There's no evidence of hostility. There's no evidence of intent. Calling something a potential threat when it's demonstrably not on a collision course, and showing no aggressive behaviour is fear-mongering. But there's also an institutional conservatism at play. Space agencies are publicly funded. Their scientists have reputations to protect. Going on record with a speculative claim that turns out to be wrong can end careers, so the incentive structure pushes toward caution, which is usually appropriate but can also suppress legitimate inquiry into edge cases. If you are hiding a craft, masking it as a comet is actually feasible in principle. You'd need to vent material that produces spectral signatures matching natural volatiles. Water, CO2, CO, simple organics. All of these can be synthesized or stored. You'd control the venting to avoid net acceleration that looks like maneuvering. You'd shape the probe to minimize radar returns and avoid geometric regularity in optical observations. You'd emit thermally like you're being passively heated by the sun. It's doable with sufficiently advanced technology. The question is whether it's plausible that someone would go to that effort. This ties into the lurker probe concept, which is a staple of SETI speculation. The idea is that an advanced civilization might seed the galaxy with autonomous probes that passively observe or collect data, remaining dormant until activated by some trigger. These probes wouldn't broadcast. They wouldn't maneuver unnecessarily. They'd just drift, watch, and wait. If you're a paranoid civilization worried about the dark forest scenario, where revealing your presence invites annihilation, lurker probes make strategic sense. You get intelligence without exposure. But here's the problem. This explanation is infinitely flexible. Any object can be a lurker probe if you're willing to posit sufficiently stealthy engineering. That makes it unfalsifiable, and unfalsifiable hypotheses aren't useful scientifically. You need testable predictions. Loeb's contribution is trying to make those predictions explicit. Look for maneuvers, look for reflections, look for emissions. If we do those searches and find nothing, the hypothesis weakens. If we find something, it strengthens. There's a policy angle here too. If there were even a 10% chance that 3i Atlas is an artifact, how should agencies respond differently? Do you prioritise close-up imaging? Do you attempt communication? Do you activate protocols for tracking and monitoring? Currently, space policy doesn't have a clear framework for this. The Outer Space Treaty addresses territorial claims and weapons in space, but it doesn't say much about how to handle potentially alien probes. SETI protocols exist for responding to detected radio signals, but they're voluntary and haven't been tested in a real scenario. Now let's acknowledge the internal debate. AstroWright Penn State astronomer Jason Wright has publicly pushed back on some of Loeb's specific claims regarding size and statistical interpretations. Wright argues that Loeb is overinterpreting noisy data, and that the size-frequency argument doesn't hold up under scrutiny once you properly account for all the selection effects and uncertainties. This isn't personal animosity. This is scientists doing what they're supposed to do, checking each other's math, questioning assumptions, refining models. The fact that there's disagreement is healthy. It means the question is being taken seriously enough to argue about. So where does the mothership hypothesis stand after tonight's Mars pass? If no maneuvers are detected, if the coma continues to behave like natural outgassing, if perihelion comes and goes without any shocking surprises, the artifact probability drops further. The Loeb scale rating should continue to decline, but unless we get close enough to image the nucleus directly, or unless we detect unambiguous technological signatures, we can't rule it out entirely. And that irreducible uncertainty is what keeps this hypothesis alive, floating in the background, a ghost in the data. Next, we turn to the third option, the one that's somehow both more plausible than a mothership and more unsettling. Part 8. Intelligence or coincidence? The dark forest debate. We need to talk about silence. Because if 3i Atlas, or Oumuamua before it, or any future interstellar visitor turns out to be artificial, the question immediately becomes, why aren't they saying hello? And the answer to that question depends on which flavour of cosmic philosophy you subscribe to. The dark forest hypothesis, popularised by Liu Cixin's science fiction trilogy but rooted in earlier game theory, goes like this. The universe is filled with intelligent civilizations, but they're all hiding. Why? Because announcing your presence is suicide. Any civilization advanced enough to detect your signal is potentially advanced enough to eliminate you as a competitor for resources. So the optimal strategy, the only strategy that ensures survival, is silence. You listen, but you never transmit. You observe, but you never reveal. The forest is dark not because it's empty, but because everyone is hiding behind the trees holding their breath. It's a grim vision, and it's worth noting that most scientists don't take it seriously as a literal description of galactic sociology. But it's a useful thought experiment for understanding why the absence of detected signals or obvious alien artifacts doesn't necessarily mean we're alone. Silence is ambiguous. It could mean nobody's out there, or it could mean everybody's out there, and they're all being very, very quiet. If the dark forest hypothesis is correct, and if 3i Atlas is an artifact, it would not broadcast. It would not maneuver in obvious ways. It would masquerade as a natural object, blend in, collect data passively, and move on. In that framework, the fact that we haven't detected technosignatures is not evidence against the artifact hypothesis. It's exactly what you'd expect. But here's the problem. This line of reasoning makes the artifact hypothesis unfalsifiable. If detection of artificial signatures would prove it's a craft, but absence of signatures is also consistent with it being a craft, then what possible observation could disprove the hypothesis? You've created a logical trap. The hypothesis survives all outcomes, and while that might be emotionally satisfying if you want to believe in alien visitors, it's scientifically sterile. Science requires falsifiability. You need to be able to say, if we observe X, the hypothesis is wrong. Loeb's approach tries to thread this needle by making the hypothesis probabilistic rather than binary. Instead of asking, is it alien? He's asking, how likely is it to be alien given the available evidence? That probability, expressed on his 0 to 10 scale, can go up or down as data accumulates. Early on, with limited information and several anomalies, you might assign a moderate probability. As more data comes in showing natural behaviour, the probability drops. If unambiguous technosignatures appear, it spikes to 10. If we get close-up images showing a classic comet nucleus, it drops to 0. The framework allows for updating, which is scientifically respectable. Most scientists would say the prior probability for any given interstellar object being artificial is extremely low, maybe 1 in a million or 1 in a billion. The burden of proof to overcome that prior is enormous. You'd need multiple independent lines of evidence all pointing toward technology. 1 anomaly isn't enough. 2 anomalies might be coincidence. 3 starts to look like a pattern, but you'd still need to rule out all natural explanations first. And that brings us to the social dynamics, the online sleuths, the leaked frames, the pareidolia. In the age of social media and instant information, every blurry image gets dissected by thousands of amateur analysts. Someone spots a pixel that looks slightly brighter than its neighbours and declares it a panel reflection. Someone notices a brightness fluctuation and calls it a course correction. The human brain is wired to find patterns, even in noise. We see faces in clouds, animals in ink blots, and conspiracies in coincidences. This isn't malicious, it's cognitive architecture. But it creates an information ecosystem where spectacular claims spread faster than careful rebuttals. A headline saying possible alien probe detected gets 1 million clicks. A follow-up saying actually it's just a comet with unusual chemistry gets 10,000. The correction never catches up to the claim, and that asymmetry poisons the discourse, making it harder for scientists to communicate nuance. SETI veterans, people who've dedicated careers to searching for extraterrestrial intelligence, tend to be cautiously optimistic about the possibility of finding alien life, while also being deeply skeptical of any individual claim. They've seen too many false alarms. Pulsars were briefly thought to be alien beacons, hence the tongue-in-cheek name LGM for little green men, until we realised they were rotating neutron stars. The WOW signal, a strong narrowband radio spike detected in 1977, has never been satisfactorily explained, but also has never repeated. Fast radio bursts were mysterious, until we found natural astrophysical sources. The pattern is always the same: initial excitement, speculation about artificial origins, eventual natural explanation. So the SETI community's stance on 3i Atlas is generally, show us the data. If there are manoeuvres, we want to see the astrometry. If there are radio signals, we want confirmation from multiple telescopes. If there are reflective panels, we want high-resolution images. Until then, it's a comet. But let's play the thought experiment. If you were designing a stealth fly-through of an alien solar system, what would you do? First, you'd arrive from out of the ecliptic, the plane where most planets orbit. That way, you're not passing through the densest part of the debris field, and you're less likely to be detected early by surveys focused on near-ecliptic objects. Second, you'd minimise energy signatures. No active propulsion if you can avoid it. No radio transmissions. If you need to vent heat, do it in a way that mimics natural thermal emission. Third, you time your approach to maximise observation time without getting too close to anything dangerous. Now, does 3i Atlas's actual trajectory match this? Profile? Not particularly. Its inclination is elevated relative to the ecliptic, but that's normal for interstellar objects since they're not bound to our solar system's angular momentum. The trajectory doesn't show any evidence of optimised observation geometry. It's not looping through the inner solar system in a way that maximises planetary encounters. It's just passing through, a straight shot in and out. If this were a designed survey, it's a pretty inefficient retry M continue edit 1. You'd want to adjust your trajectory to fly past multiple interesting targets, maybe use gravity assist to change your path. 3i Atlas is doing none of that. It's behaving like a ballistic projectile, which is exactly what you'd expect from a natural object. But the dark forest proponent would counter, maybe efficiency isn't the goal. Maybe the goal is to look natural. A trajectory that's too clever, that visits too many interesting locations, would itself be suspicious. Better to coast through on a boring path, observe what you can, and leave. The probe sacrifices data quality for operational security. Again, we're back to unfalsifiability. Every piece of evidence can be interpreted to support the hypothesis if you're creative enough. That's not science, that's storytelling. Now let's talk about echo chamber effects and algorithmic amplification. Social media platforms prioritize engagement, which means they boost content that generates strong reactions. Spectacular claims, whether they're aliens are here or government cover-up, generate strong reactions. Careful scientific analysis does not. So the algorithms push the spectacular claims to millions of users while the rebuttals languish in obscurity. This creates information bubbles where people are exposed primarily to content that confirms their existing beliefs. If you want to believe 3i Atlas is a mothership, your feed will show you dozens of posts supporting that view and very few challenging it. This isn't a new problem, but it's gotten dramatically worse in the last decade, and it makes science communication extraordinarily difficult. How do you compete with a viral tweet that says, Harvard scientist confirms alien spacecraft, when the reality is, Harvard scientist proposes hypothesis that most colleagues reject? You can't. The nuance gets flattened, the uncertainty gets erased, and people are left with a distorted picture of what science actually knows. AP News, NASA's official communications and ESA's press releases all emphasise the same message. No threat, comet-consistent behaviour, natural origin likely. These are the authoritative sources, but they're also institutional and boring. They don't trigger the emotional response that makes people share and comment. So their reach is limited compared to more sensational content. What would falsify the craft hypothesis? This is the critical question. If 3i Atlas passes perihelion and continues on a purely ballistic trajectory with no manoeuvres, that's a strong strike against it. If the chemistry continues to show only natural volatiles with no hint of industrial compounds or unusual isotopes, that's another strike. If high-resolution imaging eventually reveals a typical comet nucleus, irregular and rocky, that would effectively kill the hypothesis. If multiple future interstellar objects are detected, and they all show comet-like behaviour with a size distribution that makes sense statistically, the rare large object argument collapses. Conversely, what would confirm it? A single clear manoeuvre that can't be explained by outgassing. A radio signal, even a brief one, at an unnatural frequency. A specular reflection from a flat surface. Geometric structures visible in imaging. Any one of these would be game-changing, but they have to be reproducible, confirmed by multiple instruments, and resistant to natural explanations. One blurry image isn't enough. One questionable data point isn't enough. You need overwhelming, unambiguous evidence. The psychological closer here is important. We are pattern-seeking creatures. Our ancestors survived by detecting predators in the shadows and reading intentions from subtle cues. That cognitive machinery doesn't turn off when we're looking at astronomical data. A noisy pixel becomes a panel. A fluctuation becomes a manoeuvre. An odd chemical ratio becomes a smoking gun. We complete patterns because incomplete patterns make us anxious. We prefer wrong certainty to correct uncertainty. Understanding that about ourselves is the first step toward disciplined thinking. When you feel yourself jumping to a conclusion, pause. Ask what would need to be true for that conclusion to be wrong. Look for alternative explanations. Demand better data. Science is the art of not fooling yourself, and you are the easiest person to fool. So where does the dark forest debate leave us tonight as 3i Atlas passes Mars? If it's a lurker probe, we probably won't know unless it does something overtly artificial. If it's a natural comet masquerading as nothing in particular, we need to avoid overreading the data. The silence, the lack of techno-signatures, tells us almost nothing because it's consistent with both scenarios. What we need is positive evidence, something that unambiguously points one direction or the other, and so far that evidence points toward comet. But there's a third scenario we haven't fully explored yet, one that occupies a strange middle ground between natural and artificial. What if 3i Atlas isn't a functional object at all, but a piece of one? What if we're looking at debris from something that was destroyed long ago and far away? Part 9. The debris field hypothesis, shards from a distant cataclysm. Imagine a world dying, not slowly over geological time, but catastrophically, violently, in a matter of hours or days. Maybe it wandered too close to its parent star and tidal. Forces ripped it apart, shredding it into a stream of fragments that spiraled outward. Or maybe two planets collided, a cosmic car crash at tens of kilometers per second that vaporized the impactor and shattered the target. Or perhaps a rogue star passed through the system, gravitationally disrupting orbits and flinging worlds into chaotic trajectories. Any of these scenarios can produce exactly what we might be looking at. Large, irregularly shaped fragments enriched in certain volatiles, spinning through interstellar space on ballistic paths. This is the debris field hypothesis, and it's surprisingly plausible. We've seen planetary disruption in our own solar system. The asteroid belt might be the remnants of a planet that never formed, or possibly one that was destroyed by Jupiter's gravity. Saturn's rings are almost certainly the debris from a moon that got too close and was torn apart by tidal forces. Tidal disruption events around black holes and stars have been observed shredding objects in other systems. The physics is well understood. What's less clear is whether the resulting fragments could retain volatiles like water and carbon dioxide over millions of years in interstellar space, and whether those fragments would look like what we're seeing with 3i Atlas. Let's start with the mechanism. A tidal disruption happens when the gravitational gradient across an object becomes stronger than the object's own gravity holding it together. This is called the Roche limit. For a rocky body near a star, that limit is typically a few stellar radii. Get closer than that, and you're pulled apart. The process is violent. The object stretches, cracks, fragments. The pieces are ejected at high velocity, some falling into the star, others escaping into space. Now, if the disrupted object was an icy world, a super comet or a small planet with a substantial volatile inventory, the fragments would carry those volatiles with them. But here's the catch. The surface layers would be heated and partially vaporized during the disruption. What remains would be fragments with possibly unusual compositions, perhaps enriched in more refractory materials on the surface and more volatile materials sealed inside. Does that sound familiar? Because that's essentially the model we've been discussing for 3i Atlas, a radiation-processed crust sealing in volatiles with an unusual ratio. The tidal fragment origin for Oumuamua has been explored in multiple studies. Some researchers propose that Oumuamua's elongated shape and unusual acceleration could be explained if it were a shard from a tidally disrupted body, perhaps a nitrogen ice fragment from a Pluto-like world. The idea is that the fragment would be flat and reflective, accelerated by sunlight like a crude light sail, but entirely natural in origin. This model isn't universally accepted, but it demonstrates that the fragment hypothesis has been taken seriously for previous interstellar visitors. For 3i Atlas, the fragment model could work like this. A large icy body, maybe 1,000 kilometers across, gets disrupted near a star or giant planet. The disruption produces a debris field, a stream of fragments ranging from dust to kilometer-sized chunks. These fragments are ejected at high velocity, tens of kilometers per second, in a range of directions. Over millions of years, they spread out, but they're all moving on roughly similar trajectories because they share a common origin. Some of those fragments drift into interstellar space. 3i Atlas, in this model, is one such fragment. It's large, several kilometers across, because it was part of the core of the disrupted body. It's CO2 rich because the disruption process preferentially stripped away water from the outer layers, leaving behind the more refractory deeper ices. The crust is radiation processed from millions of years in space, which further alters the surface composition. When it enters our solar system and starts to warm up, the crust cracks and the trapped volatiles begin to vent. We see a comet-like coma, but the chemistry is skewed because the fragment's history is violent and unusual. What would the spectra show if this is correct? You'd expect to see the volatiles we're already seeing: CO2, H2O, CO. Maybe some sulfur-bearing molecules like carbonyl sulfide. You might also see unusual dust grain sizes, remnants of the disruption event that didn't fully reaccrete. The dust-to-gas ratio might be different from typical comets. JWST's observations already hint at some of this, though the data is still preliminary. The big question is, where are the companions? If 3I Atlas is part of a debris stream, there should be other fragments on similar trajectories. They wouldn't be right next to each other. Tidal disruption spreads debris over huge volumes, but statistical surveys should eventually detect other objects with similar velocities and compositions. So far, no such companions have been reported. The surveys haven't flagged a convoy, but that's not proof of absence. It just means either the companions are too small or faint to detect, or they're on slightly different trajectories that won't pass through our detection window for years or decades, or 3I Atlas is indeed a solo act. There's a population argument here. If tidal fragment streams are a significant source of interstellar objects, we'd expect to see clustering in velocity space. Objects from the same disruption event should have similar speed and direction vectors, at least initially. Over millions of years, those vectors diverge due to gravitational perturbations from passing stars and galactic tides. But for relatively young streams, say a few million years old, the clustering should still be detectable. As we accumulate more ISO detections, we can start looking for those clusters. If we find them, that's strong evidence for the debris field model. If every ISO looks completely independent, the model weakens. Now let's talk about what this means philosophically. If 3I Atlas is a fragment from a destroyed world, we're looking at forensic geology of an alien cataclysm. We're seeing the last remains of a planet or moon that died millions of years ago in a system we'll probably never identify. There's something profoundly melancholic about that. It's a tombstone drifting through the void, a piece of a world that no longer exists, carrying no life, no information, just the chemical signature of its violent end. But it's also scientifically compelling, because if we can analyse these fragments, we learn about planetary interiors in other star systems. We get direct samples of material that formed under different conditions, in different chemical environments, possibly around stars with different metallicities or ages. It's comparative planetology on a galactic scale. Every interstellar fragment is a free sample from the cosmic catalogue, and we don't even have to send a spacecraft to collect it. It comes to us. The risk communication here is important. Even if 3I Atlas is a kilometre-scale shard from a destroyed world, it's not a hazard to Earth. The closest approach is still about 270 million kilometres, even if it fragmented further as it passes perihelion, which is unlikely given how cold it is and how gentle the solar heating will be at 1.4 astronomical units. Those fragments would continue on the same hyperbolic trajectory. They wouldn't suddenly curve toward Earth. Orbital mechanics doesn't work that way. You can't change a hyperbolic orbit into an Earth-crossing orbit without a massive delta V, a change in velocity that would require either a rocket engine or a gravitational assist from a planet. Neither is happening here. But let's talk about the selection bias issue. Large fragments are rare but not impossible. If a disruption event produces a power law distribution of fragment sizes, you'll have many small pieces and a few large ones. The large ones are easier to detect, so we'd naturally find them first. As surveys improve, we should start detecting the smaller fragments, and the size distribution will fill in. The fact that we found a large one early doesn't necessarily mean large ones are common. It might just mean our surveys are still in the low-hanging fruit phase. There's also a modelling hook. If fragments come in streams, their inclinations and arrival cadence might show loose correlations. You wouldn't expect perfect alignment because the disruption event imparts a range of velocities, and millions of years of drift spread things out. But if you analyse the orbits of multiple ISOs and find that a subset of them cluster in certain parameters, that's circumstantial evidence for a common origin. We don't have enough data yet to do that analysis. 3 objects is not a statistical sample. But when we have 30 or 300, patterns might emerge. And if this model is correct, it reframes our understanding of the interstellar medium. It's not just empty space with occasional dust grains and hydrogen molecules. It's filled with debris from planetary systems, the corpses of worlds that didn't make it, drifting for eons until they encounter another star system. The galaxy is a graveyard, and we're just now starting to read the epitaphs. But there's a darker version of this story, one that's been simmering in the background of this whole conversation. What if 3i Atlas isn't an isolated fragment? What if it's the first in a series? Part 10. The Doomsday Stream. Let's go full speculative horror for a moment. Imagine that somewhere in the galaxy, maybe a few hundred or a few thousand light years away, a star system experienced a catastrophe on a scale almost beyond comprehension. A super flare from the star, 1 billion times more energetic than anything our sun produces, sterilizing the inner planets and disrupting the outer ones. Or a collision between 2 giant planets, releasing energy equivalent to millions of nuclear weapons and producing a debris field that stretches across billions of kilometers. Or a rogue star ploughing through the system at high speed, gravitationally shredding everything in its path. Whatever the mechanism, the result is a stream of debris, fragments ranging from dust to dozens of kilometers across, all ejected on similar trajectories, all moving through interstellar space at tens of kilometers per second. Millions or billions of years pass. The fragments spread out, but they're still loosely associated, a convoy of destruction drifting through the dark. And now, by sheer chance, that stream is intersecting our solar system. Oumuamua was the first, Borisov was the second, 3i Atlas is the third, and if the stream hypothesis is correct, there are more coming. Maybe dozens, maybe hundreds, some small, some large. Some we'll detect in advance, some we won't see until they're already past us. Most will miss Earth by comfortable margins, but statistically, over enough encounters, one might not. This is the Doomsday Stream scenario, and I want to be absolutely clear. This is unverified speculation. There is no official alert linking these 3 objects into a single debris stream. There is no evidence that more are coming. This is the heavy metal, worst-case keep-you-up-at-night version of the debris field hypothesis. But it's out there in the discourse, particularly in online communities that thrive on existential dread, so we need to address it directly and honestly. The first question is, does the pattern hold up? We have 3 confirmed interstellar objects in 8 years. Oumuamua in 2017, Borisov in 2019, 3i Atlas in 2025. That's an average of 1 every 2 to 3 years. Is that a trend, or is it just improved detection capabilities? The honest answer is probably detection. Capabilities. Survey technology has gotten dramatically better in the last decade. Telescopes are more sensitive, data processing is faster, automated detection algorithms are smarter, we're looking at more of the sky more often, with better tools, so we're finding more stuff. That's expected. The fact that we found 3 ISOs in 8 years doesn't necessarily mean the arrival rate is increasing. It might just mean we're finally good enough at looking to find what's always been passing through. But let's entertain the stream hypothesis. If these 3 objects shared a common origin, what would we expect to see? First, similar velocity vectors. They should be moving in roughly the same direction at roughly the same speed, accounting for perturbations from their different encounters with the solar system's gravity. Second, similar composition. They should show chemical fingerprints that suggest formation in the same environment. Third, a pattern in arrival times. If they're part of a stream, their arrivals shouldn't be random. They should cluster in time, reflecting the density distribution of the stream. Do our 3 objects meet these criteria? Let's check. Oumuamua had a hyperbolic excess velocity of about 26 kilometers per second. Borisov had about 32 kilometers per second. 3i Atlas is moving at roughly 58 kilometers per second through the inner solar system, though the excess velocity after accounting for solar gravity is lower. These aren't identical, but they're in the same ballpark. Strike 1 for the stream hypothesis, but it's a weak strike. Interstellar objects could have a range of velocities depending on their formation and ejection mechanisms. Composition. Oumuamua showed no visible coma, so we have almost no compositional data. Some models suggest it might be nitrogen ice. Others propose hydrogen ice or even a dust bunny. Borisov was a classic comet, water-rich. with a composition similar to solar system comets. 3i Atlas is CO2 rich, which is different from both, so no clear pattern. Strike 2 and this one's stronger. If they're from the same disruption event, you'd expect more similarity. Arrival timing? Oumuamua in October 2017, Borisov in August 2019, but closest approach in December. 3i Atlas discovered July 2025, closest approach to Mars today, October 3rd. The intervals are roughly 2 years, then 6 years. That's not a regular pattern. If they're part of a stream, the stream is either very spread out or very diffuse. Strike 3. So statistically, the case for these 3 objects being part of a single debris stream is weak. They look more like independent arrivals from different systems, which is what most astronomers believe. But, and this is important, our sample size is still tiny. 3 data points is barely enough to establish a baseline, let alone detect patterns. We need more detections. And that's where the Vera C. Rubin Observatory comes in. Rubin, formerly known as LSST, the Large Synoptic Survey Telescope, is set to begin operations soon. It will survey the entire visible sky every few nights, detecting objects far fainter than current surveys can see. Models predict Rubin will detect interstellar objects at a rate of 1 per year, possibly more. Within a decade we could have dozens of confirmed ISOs. That's when we'll be able to do real statistics. That's when patterns, if they exist, will emerge. If the stream exists, here's what we'd look for. Multiple ISOs detected over the next few years with similar velocity vectors and compositional fingerprints. Micrometeoroid impacts on spacecraft showing unusual density or composition patterns that correlate with the stream's predicted trajectory. Infrared background anomalies, slight variations in the diffuse IR glow of the sky that could indicate an unusual concentration of dust. None of these have been reported yet. Searches for such signals are ongoing, but they're challenging because the sky is noisy and the signals would be subtle. Let's talk about how survey improvements change the equation. Rubin will detect objects down to magnitude 24 or 25, which is incredibly faint. For context, the faintest stars visible to the naked eye are about magnitude 6. Each step in magnitude is a factor of 2.5 in brightness, so magnitude 25 is about 400 million times fainter than naked eye visibility. At that sensitivity, Rubin will see small asteroids, distant comets, and yes, interstellar objects that previous surveys would have missed entirely. This doesn't just increase the detection rate, it changes the size distribution of detected objects. Currently we're biased toward large or highly active objects because those are bright. Rubin will detect smaller, fainter objects, filling in the low end of the size distribution. If we start seeing dozens of small ISOs for every large one, that would match expectations for natural ejector populations. If the ratio stays skewed toward large objects, that would be genuinely strange and would lend some support to Loeb's statistical arguments. Now, the narrative escalation. If the stream exists, could later fragments be larger or closer? In principle, yes. Debris streams aren't uniform. They have density variations, clumps and gaps, depending on the initial disruption geometry. If we're encountering the leading edge of a stream now, the main body could arrive in a few years or decades. But larger or closer doesn't automatically mean dangerous. Even a 10-kilometre fragment passing at the same distance as 3i Atlas, about 270 million kilometres from Earth, is no threat. You'd need an impact trajectory, an orbit that actually intersects Earth's path, and that's extraordinarily unlikely for an object on a hyperbolic orbit from interstellar space. The geometry just doesn't favour it. Planetary defence, the people, who worry about asteroid impacts for a living, focus almost entirely on near-Earth objects that are gravitationally bound to the Sun. Those are the threats we can track, predict, and potentially deflect. Interstellar objects are a different category. Their arrival is essentially random. We might get a few weeks or months of warning depending on how bright they are and when surveys catch them. But deflection isn't realistic for something moving at 50 or 60 kilometers per second. Our current technology can barely handle slow-moving asteroids in predictable orbits. An ISO streaking through the inner solar system at interstellar velocities. We'd watch it pass and hope for the best. But let's be absolutely clear. AP News, NASA and ESA all emphasise that 3i Atlas poses no threat. The closest approach to Earth is more than 250 million kilometres. Even if it fragmented, even if there were unseen companions, the orbital mechanics don't allow for a sudden course change that would threaten our planet. The doomsday scenario requires not just a stream of debris, but a stream of debris with a trajectory that specifically targets Earth. The probability of that is vanishingly small. Space is vast. Earth is tiny. Hitting us by accident would require apocalyptically bad luck. So where does the stream hypothesis stand? It's testable, which is good. Over the next few years, if we detect multiple ISOs with correlated parameters, the hypothesis gains credibility. If every ISO looks independent, the hypothesis fades. It's speculative, which is fine in science as long as you label it clearly. And it's not threatening in any immediate sense, though it would change how we think about the interstellar environment and might eventually require updates to planetary defence strategies. The philosophical beat here is profound. If the stream exists, it means the galaxy is more dynamic than we realised. Catastrophic events in distant star systems have consequences that propagate across light years and eons. The universe isn't a collection of isolated systems. It's interconnected, violent and full of scars. A stream of debris passing through our solar system would be a reminder that we're part of that larger, more chaotic cosmos. We're not safe in a bubble. We're drifting through the wreckage of worlds that didn't survive. But testable predictions make this more than philosophy. Watch for another interstellar detection in the next few years. If it's CO2 rich like 3I Atlas, pay attention. If its velocity vector is similar, pay closer attention. If we start seeing a pattern, then the stream hypothesis moves from speculative to plausible. Until then, it's a possibility, not a probability. And that brings us to the information gap, the delay between observation and disclosure, and why some people are convinced the data is being withheld. Part 11. The Hidden Data War. Let's talk about what happens between the moment a telescope captures data and the moment you read about it in a headline. Because that gap, that frustrating, anxiety-inducing lag, is where conspiracy theories are born. Here's the normal pipeline. An observatory, let's say Hubble or JWST or one of ESA's Mars orbiters, observes a target. The data comes down as raw photons converted to digital signals. That raw data is full of artifacts, hot pixels from cosmic ray hits, instrumental noise, calibration drifts, systematic errors. Before it can be scientifically useful, it needs to be processed. That means applying calibration frames, subtracting backgrounds, correcting for atmospheric or instrumental distortions, and converting the signal into physically meaningful units like brightness or spectral flux. This processing takes time. Hours for simple imaging, days for complex spectroscopy, weeks if the data is unusual or requires custom pipelines. Once the data is reduced, the science team analyses it. They fit models. They compare to theoretical predictions. They check for consistency with other datasets. They write it up, usually as a paper or a technical memo. Then comes peer review, where other scientists read the draft, check the methods, and suggest revisions. This can take weeks to months. Finally, if all goes well, the paper is published in a journal or posted as a preprint on Arxiv. Alongside this, there's the public relations track. If the results are exciting or newsworthy, the institution might issue a press release. That press release gets picked up by science journalists who write articles. Those articles get shared on social media, and eventually the information reaches the public. The whole process, from observation to headline, can take anywhere from a few weeks to several months, sometimes longer. This is normal. This is how science works. It's methodical, careful, and slow. But to someone watching from the outside, especially someone excited or anxious about what might be discovered, it feels like a cover-up. They observed it weeks ago. Where are the results? What are they hiding? The answer, 99.9% of the time, is nothing. They're just doing science, which is boring and meticulous and doesn't move at the speed of Twitter. But, and this is important, institutional PR versus online leaks does create a perception gap. We saw this with Oumuamua. Amateur astronomers and data enthusiasts were analysing publicly available astrometry and speculating about the object's properties days before official press releases came out. When those press releases finally arrived, they sometimes contradicted or downplayed the more sensational interpretations. To some people, that looked like damage control. They're trying to calm us down because they know something we don't. In reality, it's just the difference between preliminary analysis and vetted conclusions. Early interpretations are often wrong. Data gets revised, models get updated, the official Channels wait until they're confident before making statements, which is responsible but slow. The online community moves fast, trading speed for accuracy. Both have value, but they operate on different timescales and with different incentives. For 3i Atlas, NASA's Goddard Space Flight Center published a nugget, a short summary article about WST's observations. It highlighted the unusual CO2-rich coma and the asymmetric shape. That's transparency. They're telling us what they found. But it's a summary, not the full data set. The full spectral data, the calibrated observations, those are being prepared for a journal article. When that article is published, other scientists will be able to download the data, run their own analyses, and check the conclusions. That's how the system is supposed to work. ESA similarly confirmed that Mars Express and ExoMars Trace Gas Orbiter would observe 3i Atlas during the October 1st through 7th window. They've posted updates on social media and their websites. But processed images and spectra, those will come later, after the data is reduced and validated. Again, this is normal. But the lag feeds anxiety. Now let's talk about media amplification. Sensational pieces, whether they're pro-alien or hardcore debunking, spread faster than nuanced science. A headline that says alien mothership approaches Mars gets shared 1 million times. A headline that says interstellar comet shows unusual chemistry, scientists investigating gets shared 10,000 times. The asymmetry is built into human psychology. We're drawn to novelty and threat. A careful, balanced analysis doesn't trigger the same emotional response, and this creates an ecosystem where the loudest voices dominate. You get outlets that lean into the alien angle because it drives traffic. You get other outlets that lean into debunking because contrarianism also drives traffic. The actual scientific middle ground, we don't know yet, here's what we're doing to find out, gets squeezed out. It's not exciting enough for the first group and not definitive enough for the second. Why do statements like no threat get repeated so often? Because public reassurance during rare events is part of the job for agencies like NASA and ESA. When something unusual happens, people get nervous. They imagine worst-case scenarios. It's the agency's responsibility to say, clearly and repeatedly, this is not dangerous. Even if it feels redundant to people who've been following closely, there are always new people hearing about it for the first time who need that reassurance. Now let's talk about evidence literacy, because this is where individuals can take control. When you see a claim about 3i Atlas, ask yourself, where did this information come from? Is it a peer-reviewed paper? That's gold standard. Is it a preprint on Arxiv? That's still good. It means scientists are willing to put their names on it and face scrutiny. Is it a press release from a reputable institution? That's decent, though press releases sometimes simplify or hype results. Is it a blog post, a tweet, a YouTube video? That's where you need to be careful. Not all of these are wrong, but they're less filtered, more prone to speculation and error. Citations matter. This document you're hearing is full of citations pointing back to sources, NASA pages, ESA releases, Arxiv preprints, AP news articles. That's how you build a chain of evidence. If someone makes a claim and can't or won't cite a source, that's a red flag. Maybe they're right, but you have no way to verify it, so you should hold that claim lightly. A.V. Loeb's posts and the pushback from people like Jason Wright are part of science in public. It's not a bug, it's a feature. Scientists disagree. They challenge each other's assumptions and methods. That friction is how errors get caught and ideas get refined. Seeing the disagreement doesn't mean the field is in chaos. It means the process is working. When everyone agrees immediately, that's when you should worry, because it might mean no one's actually checking the math. The data war framing is mostly a tempo mismatch. Social media wants answers now. Telescopes and scientists work on timescales of weeks to months. That gap creates frustration, and frustration creates speculation. But the solution isn't to speed up science, because rushed science is bad science. The solution is to accept that uncertainty is part of the process, and that patience is a virtue. That said, if you want to follow along in real time, here's what to do. Bookmark the Minor Planet Center's page for 3i Atlas. That's where new astrometry gets posted as observatories submit it. Check Arxiv regularly for preprints with 3i or Atlas, or Interstellar in the title. Follow NASA, ESA and major observatories on social media, but read past the headlines. And most importantly, remember that absence of news isn't evidence of cover-up. Sometimes there's just no news yet. into that vacuum, inevitably, rush the conspiracies. Part 12. The Conspiracy Web. Alright, buckle up. We're about to catalogue some of the wilder claims circulating about 3i Atlas, and I want to be crystal clear. These are speculative, unverified, and in most cases, demonstrably false. But they're out there, people believe them, and ignoring them doesn't make them go away. So let's shine a light and see what scurries. First, the secret Mars probe fly-through video. The claim is that one of the Mars orbiters, usually Mars Reconnaissance Orbiter or Mars Express, captured high-resolution images or video of 3i Atlas during closest approach, and those images show something unambiguous: geometric structures, panel arrays, maybe even surface markings that look artificial. These images exist, the conspiracy goes, but they're being withheld from the public because releasing them would cause panic or reveal that world governments have known about extraterrestrial visitors for years. Let's break this down. First, no such images have been publicly released or leaked. Second, if they existed and showed something genuinely shocking, keeping them secret would be nearly impossible. Space agencies employ thousands of people, scientists talk to each other, data gets shared across international collaborations. The idea that a smoking gun image of an alien spacecraft could be captured and then suppressed without a single whistleblower, a single leaked file, strains credulity. Third, the geometry of tonight's encounter makes high-resolution imaging difficult. 3i Atlas is millions of kilometers from Mars at closest approach. Even MRO's high-rise camera, which is phenomenal for imaging the Martian surface from orbit, would struggle to resolve fine details on a small, distant, fast-moving object surrounded by a coma. So the premise that such a video exists is already questionable, but let's say hypothetically that MRO did image 3i Atlas, and the image showed something weird. A glint that might be a reflection from a flat surface. A brightness variation that doesn't match rotation models. What would happen? The science team would analyse it carefully. They'd check for instrumental artifacts. They'd model natural explanations. If they couldn't explain it, they'd publish, because unexplained data is scientifically valuable. The idea that they'd sit on it indefinitely doesn't match how science actually works. Careers are built on discoveries, not cover-ups. Second conspiracy: military intercept planning. The claim here is that the Department of Defense or equivalent agencies in other countries are planning to intercept 3i Atlas with a spacecraft, either to study it up close or to destroy it if it's deemed a threat. Variations of this claim suggest that classified military sensors have detected anomalous behaviour from the object, fast movers, acceleration patterns, and that preparations are underway for a response. Reality check. No public agency has announced an intercept mission. Earth's closest approach to 3i Atlas is about 270 million kilometres in December. Launching a spacecraft to cover that distance and match velocities with an object moving at over 50 kilometres per second would require absurd amounts of fuel and years of travel time. It's not happening on the timescale we're talking about. Moreover, 3i Atlas poses no threat. It's not on a collision course. There's no strategic or defensive reason to intercept it. The Retry-M Continue Edit only reason to send a spacecraft would be scientific curiosity, and those missions take years to plan and approve. We're not launching anything on a few months' notice. Now, the fast movers detected by DoD sensors. The Department of Defense does operate space surveillance networks that track objects in orbit and beyond. Some of that data is classified because the sensors' capabilities are sensitive. But the idea that they've detected something about 3i Atlas that civilian astronomers haven't is unlikely. The object's trajectory has been tracked by dozens of observatories worldwide. Its position and velocity are known to high precision. If it were manoeuvring, the civilian astrometry would show it. You can't hide orbital mechanics from math. Third cluster of claims. Various online communities have been analysing supposed leaked frames, blurry images or video snippets that allegedly show 3i Atlas in detail. Some claim to see geometric patterns, regular shapes that don't occur naturally. Others point to brightness variations that look like running lights or energy signatures. These images circulate on forums, Discord servers and subreddits dedicated to UFOs and conspiracy theories. Here's the problem. Blurry images are Rorschach tests. Your brain fills in the gaps. You see what you expect or want to see. This is called pareidolia, the tendency to perceive meaningful patterns in random or ambiguous stimuli. It's why we see faces in clouds, Jesus in toast, and spacecraft in noisy pixel data. Without proper metadata, calibration information, and source verification, these images are worthless as evidence. They could be misidentified solar system objects. They could be instrumental artifacts. They could be outright fabrications. Unless the source can be traced back to an actual observatory with documented observation parameters, treat them as entertainment, not data. The Daily Beast and The Guardian have both run pieces on 3i Atlas, and they illustrate how narratives bifurcate. The Daily Beast leaned into the alien speculation, quoting Loeb prominently and emphasising the strangeness. The Guardian, particularly in articles featuring quotes from mainstream astronomers, pushed back, stressing the comet hypothesis and warning against sensationalism. Both are legitimate outlets, but they're targeting different audiences and framing the story differently. This isn't coordinated misinformation. It's just journalism responding to market pressures. The Daily Beast knows its readers want the what if it's aliens angle. The Guardian's science section knows its readers want the here's what scientists actually think angle. Both perspectives exist in the public conversation, and neither is a complete picture on its own. Now let's address the big question. If someone genuinely wanted to hide a discovery, could they? Let's say JWST detected unambiguous technosignatures in 3i Atlas's spectrum, a narrow emission line at a frequency used by human technology but not produced naturally, or thermal emissions that indicate active power generation. Could NASA suppress that? The short answer is no, not for long. Here's why. JWST data goes through multiple pipelines. The Space Telescope Science Institute processes it. Multiple co-investigators on the observing proposal have access. Data is archived and, after a proprietary period becomes publicly available, hundreds of scientists would need to be in on the secret. And scientists are terrible at keeping secrets, especially exciting ones. The incentive structure of academia rewards discovery, not silence. Publishing "We found aliens" would win you a Nobel Prize. Agreeing to bury that information forever would win you what, exactly? A pat on the back from a shadowy government agency that may or may not exist. Moreover, 3i Atlas has been observed by independent facilities, not just NASA assets. ESA's Mars orbiters, ground-based telescopes in Chile, Hawaii, Spain, Arizona, amateur astronomers with backyard rigs. The Minor Planet Center has received thousands of position measurements from hundreds of contributors. If NASA tried to suppress anomalous data, someone else would have seen it and published independently. You can't control that many observation channels. But let's say, for argument, that all the major institutions coordinated to suppress a discovery. That would require a conspiracy spanning multiple countries, dozens of organizations and thousands of individuals. Conspiracy theories of that scale fall apart under their own weight. Someone talks, someone leaks. Someone's conscience won't let them stay silent. The bigger the secret, the shorter its half-life. Offer a falsifiable hook. If a fly-through video existed and showed something remarkable, when would we expect it to leak or be officially released? Based on previous timelines for Mars orbiter data, preliminary results often appear within weeks, full datasets within months. So if we're into November, December and still no images, one of two things is true. Either the images don't exist or they don't show anything surprising. Both point away from the conspiracy. Psychological closure here is critical. We're wired to complete patterns. When information is incomplete, our brains generate possibilities to fill the void. That's a survival mechanism. In ancestral environments, assuming the rustle in the grass was a predator kept you alive more often than assuming it was wind. But in the information age, that same mechanism makes us vulnerable to conspiracy thinking. Every data gap becomes a potential cover-up. Every delay becomes suspicious. Every official statement that says nothing to worry about sounds like, that's exactly what they'd say if there was something to worry about. The antidote is twofold. First, understand the mechanisms you can recognize when it's happening to you. When you feel yourself building an elaborate explanation for why data is being withheld, pause and ask whether the simplest explanation is just that the data takes time to process. Second, demand evidence proportional to the claim. Extraordinary claims like world governments are hiding proof of aliens require extraordinary evidence. A blurry image and a hunch don't cut it. So where does the conspiracy web leave us? Most of these claims are unfounded. Some are based on misunderstandings of how space agencies work. are fewer deliberate fabrications designed to generate clicks or sell merchandise. But the reason they persist isn't because people are stupid. It's because the information landscape is confusing, the official timelines feel slow, and the possibility of something extraordinary is genuinely exciting. We want there to be aliens. We want the universe to be more than just rocks and gas. And that desire makes us vulnerable to narratives that promise revelation. When the smoke clears, when Mars data is fully processed and released, when perihelion passes and we have even more observations, most of these conspiracies will quietly fade. The believers will move on to the next mystery. The skeptics will say, "I told you so." And scientists will keep doing what they do, collecting data, testing models, revising hypotheses. It's not as dramatic as a cover-up, but it's how we actually learn things. Speaking of which, scientists are still disagreeing about what this thing is. Let's hear the best arguments from both sides. Part 13. Philosophers and physicists react. The scientific community is not a monolith. Walk into a room of astronomers and ask them about 3i Atlas, and you'll get a spectrum of responses that range from, obviously a comet, move on, to, let's keep our options open until we have definitive proof. This disagreement isn't a weakness. It's how science is supposed to function. Ideas compete. Evidence arbitrates. Let's map the landscape. First, the empiricist camp. These are the scientists who follow in the tradition of researchers like David Jewett and Karen Meach, people who've spent careers studying comets and asteroids and know the natural population intimately. Their position is straightforward. Data first, natural until proven otherwise. They look at JWST's spectroscopy showing water, carbon dioxide, carbon monoxide and carbonyl sulfide, all natural volatiles, and they say, comet. They look at the asymmetric coma and say, jetting, which is normal. They look at the weak non-gravitational acceleration and say, probably balanced jets or high mass, both of which we've seen before. For the empiricists, the bar for claiming something is artificial is enormously high, and rightly so. We've been fooled before. Pulsars, when first discovered in 1967, were so regular that Jocelyn Bell and Anthony Hewish jokingly called the signal LGM-1 for little green men. Turned out they were rotating neutron stars, natural but exotic. The WOW signal in 1977 looked like a narrow band transmission from space, exactly what SETI was searching for. It was never explained and never repeated, so it remains a curiosity but not proof of anything. Fast radio bursts were mysterious until we found natural astrophysical sources, magnetars and other exotic objects. The pattern is always the same. Something looks weird. People speculate. Natural explanations emerge. The weird thing becomes a new category of natural object. So the empiricist stance is, let's not repeat that cycle. Let's exhaust natural explanations before invoking technology. And for 3i Atlas, natural explanations are working just fine. The chemistry is unusual but explicable. The size and mass are uncertain but plausible. The trajectory is hyperbolic, confirming interstellar origin, but shows no signs of manoeuvring. Comet fits. Done. Then there's the pluralist or possibilist camp, where Avi Loeb is the most prominent voice but not the only one. Their position is more nuanced than the headlines suggest. They're not claiming 3i Atlas is definitely artificial. They're saying that anomalies, even if individually resolvable through natural mechanisms, accumulate to a point where it's scientifically responsible to consider alternatives. And they're arguing that the stigma around discussing extraterrestrial artifacts has caused the community to underweight that possibility. Loeb's Loeb scale is, in his view, an attention allocator. If something scores a 4 out of 10, that doesn't mean probably alien. It means weird enough that we should dedicate more observational resources to rule out artificial origins definitively. It's a triage tool. And his point is that if we never look for artificial signatures, because we assume everything is natural, we'll never find them even if they're there. The philosophical stake here is profound. What counts as sufficient evidence for an extraordinary claim in astronomy? If you demand absolute proof, you'll never accept anything because astronomy is fundamentally uncertain. We can't bring these objects into the lab. We can't run controlled experiments. We infer from light and gravity, and inferences are always probabilistic. So the question becomes, at what probability threshold do you start taking an explanation seriously? For most scientists, the threshold for "this might be artificial" is extremely high, maybe 99% confidence or higher. For Loeb it's lower, maybe 60 or 70%. That's a fundamental disagreement about priors and Bayesian updating. Neither position is obviously wrong. They're different risk assessments. The empiricists want to avoid false positives, crying alien when it's just a rock. The pluralists want to avoid false negatives, dismissing something genuinely important because it didn't fit expectations. Now let's talk about institutional fatigue. Some researchers bristle at the alien question, not because they're closed-minded, but because it's been asked and answered so many times with natural explanations that it feels like a distraction. Every weird comet, every unusual asteroid, every unexplained signal gets dragged through the could it be aliens mill. Most of the time the answer is no, and the media coverage and public speculation create noise that makes it harder to do actual science. Telescopes get flooded with observation requests. Email inboxes fill with questions from journalists and amateurs. Time that could be spent on research gets spent on public engagement and damage control. This creates a perverse incentive. The more you engage with the alien question publicly, the more attention you attract, which creates more demands on your time. So some scientists just refuse to engage. They ignore the speculation and focus on the natural models. That's not a cover-up, it's time management. But it does create the perception that mainstream scientists are dismissive or dogmatic, which fuels the conspiracy thinking we discussed earlier. Historical analogues are instructive. Remember the canals of Mars? In the late 1800s and early 1900s, some astronomers reported seeing linear features on Mars that looked like artificial channels. Turned out to be optical illusions and low-resolution artifacts. Pulsars, as mentioned, were briefly thought to be beacons. More recently, in 2020, an object designated 2220 CSO was initially thought to be an asteroid, but turned out to be a human rocket booster from the 1960s. The orbital dynamics eventually revealed its artificial origin, but it took weeks of analysis. These analogues teach humility. Sometimes nature is weirder than we expect, and what looks artificial is just a new natural phenomenon we haven't catalogued yet. But sometimes, rarely, the weird thing turns out to be human-made, as with 2020 SO. And the leap from human-made to alien-made is enormous, but not logically impossible. It's happened 0 times in confirmed history, which makes the prior very low. But 0 out of a small sample doesn't mean it can never happen. Policy implications are worth considering. If 3i Atlas were artificial, even if benign, it would raise questions about space law, traffic management and contact protocols. The Outer Space Treaty, signed in 1967, governs activities in space and treats celestial bodies as the common heritage of humankind. But it was written assuming human actors. If an object is confirmed to be of extraterrestrial origin and potentially functional, who has jurisdiction? Who decides whether to attempt communication? What are the risks of active attempts to signal? SETI has a set of post-detection protocols that recommend international consultation before responding to any detected signal, but those are voluntary and haven't been tested, and they apply to radio signals, not physical objects. If 3i Atlas were a probe, and if it were actively collecting data, should we try to communicate? Wave at it with lasers? Send radio messages? Or observe quietly and avoid drawing attention? These are not trivial questions, and we don't have consensus answers. The science communication lesson here is about managing public wonder without overstating certainty. The public deserves accurate information. They deserve to know when something is genuinely unusual, and when it's being hyped for clicks. But they also deserve to feel excited about discovery, to participate in the process of figuring things out. Walking that line is hard. Say too much about the alien possibility, and you feed speculation. Say too little, and you seem evasive. The best approach is probably transparency about uncertainty. Here's what we know. Here's what we don't know. Here's what we're doing to find out. Here's why some scientists think X, and others think Y. Where do most professionals converge today? On the base case being a CO2-rich interstellar comet, but with an openness to surprises. Keep observing. Keep analysing. If something genuinely anomalous shows up, investigate it rigorously, but don't prejudge the data. Let the observations guide the conclusions, not the other way around. On the rating dispute, the record is clear. Loeb initially commented through various channels in early August, with numbers that got quoted as 6 out of 10. Later, in his own Medium posts as JWST data came in, he revised to 4 out of 10. That's exactly how the system is supposed to work. Scores move with evidence. As we get more data, especially if 3i Atlas continues to behave like a comet through perihelion, the score should continue dropping. If it behaves anomalously, the score might rise again. The framework is provisional, iterative, and data-driven. Whether you agree with the specific numbers is less important than the principle that our confidence should update as evidence accumulates. So the philosophers and physicists leave us with a split decision. Most lean toward comet. A minority argues for elevated vigilance. The evidence so far favours the majority, but the door isn't sealed shut, and tonight's Mars encounter might give us the data to close it one way or another. So what actually came back from the Mars window? Part 14. The Mars encounter results. Alright, let's talk about what we're looking for from tonight's Mars encounter, and what the realistic expectations are. Because by the time you're hearing this, 3i Atlas is either already past its closest approach to Mars or approaching it within hours, and the spacecraft instruments are either capturing data or have already captured it. But the processed results, those won't be public for days or weeks at minimum. So this section is part debrief, part preview of what to watch for when the data drops. First, coma asymmetry shifts with solar angle. JWST observed an asymmetric coma back in August. That asymmetry tells us the outgassing isn't uniform. There are jets, preferred directions where material is venting more strongly. As 3i Atlas moves through its orbit and the angle between the Sun, the comet, and our observing position changes, we should see the coma shape evolve if it's driven by solar heating. Mars orbiters, observing from a different geometry than Earth-based telescopes, can check if the asymmetry is behaving as predicted. If the coma shape matches thermal models, that's strong evidence for natural comet behaviour. If it doesn't, if the jets are pointing in directions that don't correlate with sunlight, that's an anomaly worth investigating. Second, hints of jet collimation or outbursts. Collimated jets are narrow, focused streams of gas and dust, as opposed to diffuse, broad outflows. Seeing collimation tells us something about the nuclear structure. Maybe there are fractures or vents channeling the flow. Outbursts are sudden, brief increases in activity. They can happen when subsurface pockets of volatile material suddenly breach the surface. Both phenomena are well documented in solar system comets. If we see them in 3i Atlas, it strengthens the comet hypothesis. If we don't, that's not necessarily alarming, but it's worth noting. Third, thermal irregularities versus expectations. Every object in space emits thermal radiation based on its temperature. That temperature depends on how much sunlight it absorbs and how efficiently it radiates heat. For a comet, most of the thermal emission comes from dust grains in the coma, which are heated by sunlight. If infrared observations show the thermal profile matches what you'd expect for dust at that distance from the Sun, great. If there are hot spots or cold spots that don't make sense, that's interesting. Could be natural, pockets of exposed ice versus dust-covered regions. But it's worth modelling carefully. If ESA or NASA release early findings, here's what we should look for in their statements. First, language. Are they confident in calling it a comet, or are they hedging? Phrases like consistent with cometary activity or no anomalies detected indicate they're not seeing anything shocking. Phrases like unusual features or further analysis required might indicate something interesting. Second, specifics. Did they measure a rotation period? Did they detect spectral lines beyond what JWST saw? Did they observe any changes in activity level? Third, comparisons. Are they explicitly comparing 3i Atlas to known comets and finding similarities, or are they emphasizing differences? Cross-compare to JWST's baseline observations from August 6th. Did the CO2 to H2O ratio hold steady, or did it shift? If it shifted toward more water, that supports the radiation crust model we discussed. The crust is heating up, and deeper, water-rich layers are starting to outgas. If it stayed stubbornly CO2-dominated, that's more consistent with intrinsic compositional strangeness. Was carbonyl sulfide, OCS, still detectable? That's a fragile molecule, easily broken down by UV radiation. Its persistence would tell us something about the coma's shielding or the nucleus's activity patterns. Does the non-gravitational acceleration constraint tighten after the Mars pass? With more arc length, more time observing the object's trajectory, the orbit fits become more precise. If the acceleration is still weak but now measured with higher confidence, the heavy nucleus model gains support. If the acceleration suddenly increases or shows directionality inconsistent with outgassing, that's when alarms start ringing. Which hypotheses survive? Let's scoreboard this honestly. The comet hypothesis is strengthened by stable, natural behaviour. If the Mars data shows nothing surprising, if the comet evolves predictably, if the spectra remain volatile rich without any technosignatures, comet wins. The artifact hypothesis needs manoeuvres or artificial signatures. Did we see any? Based on trajectory data available so far, no. If that holds through the full Mars pass analysis, the artifact probability drops maybe from lobes 4 out of 10 down to 2 or 1. The debris field hypothesis is harder to test with a single object. We'd need to detect companions or see evidence of unusual fragmentation, and neither seems likely from this encounter. Note any surprises. If there's a dust grain size distribution that's different from typical comets, that's interesting. If there are unexpected emission lines, molecules we didn't anticipate, that's worth a deep dive. If there's a brightness spike, a sudden increase in reflected light that doesn't correlate with known processes, that could be an outburst or it could be something stranger. Communication dynamics matter. How quickly do teams publish? If results appear on our quill within a week or two, that suggests either the data was straightforward to analyse or something surprising prompted rapid write-up. If it takes months, that's normal but less exciting. Watch for conference talks. The American Astronomical Society has meetings every few months. The European Astronomical Society hosts conferences. Division for Planetary Sciences of the AAS is particularly relevant. If researchers present 3i Atlas results at these venues before formal publication, the abstracts and slides often get shared publicly. Address rumours versus posted data. This is critical. If someone claims ESA detected a metallic reflection, where's the data? If it's not on ESA's website, not in a preprint, not confirmed by multiple sources, treat it as a rumour. Rumours might be based on misunderstandings, deliberate fabrications, or premature leaks of preliminary data that later gets revised. Wait for official sources or peer-reviewed publications before accepting claims. Cliffhanger option, because we have to be intellectually honest. If a puzzling glint or reflectance spike gets detected, something that lasts a few seconds or minutes and doesn't obviously fit thermal or rotation models, what would that mean? First, rule out instrumental artifacts. Cosmic ray hits can create bright pixels. Scattered light from the Sun or Mars can create transient reflections. Second, rule out natural explanations. Ice grains in the coma can produce specular reflections if they're oriented correctly. Tumbling fragments can catch sunlight at specific angles. Third, if those are ruled out, model artificial scenarios. A flat, reflective surface rotating into view would produce a predictable light curve. Compare the observation to that prediction. If it matches, you've got something worth a deeper look. If it doesn't, back to natural explanations. Confirmation would require seeing the effect repeat. One glint is a curiosity. Multiple glints with a regular period matching a rotation is a pattern. And patterns are where you start building hypotheses. But let's be real. The most likely outcome from tonight's Mars pass is this: data confirming what we already suspected. 3i Atlas is a large CO2-rich interstellar comet. It's active, it's unusual, it's scientifically valuable. But it's not a mothership, it's not a fragment from a doomsday stream heading our way. It's just nature being weird, which is the best kind of weird because it means we get to learn something new about how comets form in other star systems. We'll know more in the coming weeks. And when we do, the story will continue. So what happens after tonight? Part 15. The Future Sky. Awaiting the fourth visitor. Let's anchor ourselves in what's secure. 3i Atlas is interstellar, that's not in dispute. Its hyperbolic orbit, its velocity, the astrometry from dozens of observatories, all confirm it came from beyond our solar system. It poses no threat to Earth. The closest approach in December will be about 270 million kilometres, more than 600 times the distance to the Moon. Even if every pessimistic assumption about its size and composition turned out to be true, it's not on a collision course. Perihelion, its closest approach to the Sun, happens around October 30th, 2025, at about 1.4 astronomical units. That's our next major observational window, and it might answer some of the lingering questions about activity and composition. What have we learned? The biggest takeaway is that CO2-rich interstellar objects exist. Before 3i Atlas, we had one interstellar comet in our catalogue, Borisov, which was water-rich and looked like a solar system comet that happened to be passing through. Now we know the interstellar population includes chemistry we don't see commonly in our own comet reservoirs. That's not shocking if you think about it. Different star systems have different formation conditions, different disk temperatures, different chemical abundances. A comet that formed around an M-dwarf red dwarf star would experience different thermal regimes than one that formed around a sun-like G-star. We should expect diversity, but expecting it and observing it are different. 3i Atlas gives us our first confirmed data point. Second lesson, activity doesn't guarantee a large non-gravitational push. The naive assumption is that if you see a coma, you should see strong acceleration from outgassing. 3i Atlas shows that's not always true. Balanced jets, high mass, or some combination can suppress the net acceleration even when the object is visibly active. This matters for modelling and orbit prediction. If future surveys detect faint, active interstellar objects, we can't assume their trajectories will be significantly perturbed by outgassing. We need to measure carefully. What's next observationally? Perihelion on October 30th is the big one. Solar heating will peak. If the object is going to have an outburst, that's when. If the CO2 to H2O ratio is going to shift, perihelion is where we'd see it. Earth-based telescopes will be watching. Space telescopes, if they can get observing time, will be watching. This is our last best chance to characterise this visitor before it heads back into the dark. Beyond Earth, there are other platforms. NASA's Psyche mission, launched in 2023 and en route to the metallic asteroid Psyche, is in a position where it might be able to observe 3i Atlas from a different solar system vantage point. ES's JUICE mission, as we mentioned earlier, could offer long baseline observations from its trajectory toward Jupiter. These aren't guaranteed. Mission teams have primary objectives, and interstellar visitors are targets of opportunity. But if the science case is strong enough, time might be allocated. Long arc dynamics will continue to improve as we track 3i Atlas further from the Sun. Every additional month of observations adds to the orbital solution, tightening error bars on the trajectory and improving our ability to detect subtle, non-gravitational forces. If there are any hidden accelerations, any small maneuvers that current data can't resolve, continued tracking will reveal them, or confirm their absence. The Rubin era is about to change everything. The Vera C. Rubin Observatory, with its 8.4-metre mirror and enormous field of view, will survey the entire visible sky repeatedly, detecting transient and moving objects far more efficiently than current facilities. Models predict Rubin will find one interstellar object per year, maybe more. Within a decade, we could have a sample of 30 to 50 confirmed ESOs. That's when statistics become meaningful. We'll be able to map size distributions, compositional trends, velocity vectors. We'll know if 3i Atlas is an outlier, or if CO2-rich comets are common. We'll know if large objects like this are rare flukes, or if our early detections just happen to catch the bright ones. Rubin will also detect smaller objects. Right now our surveys are biased toward large or highly active ISOs, because those are easiest to spot. With Rubin's sensitivity, we'll start seeing the small stuff, the 100-metre boulders, the 10-metre pebbles. If the size distribution matches theoretical predictions for natural ejecta, great. If it doesn't, if there are unexpected clumps or gaps, that's a new puzzle. Let's scoreboard where each hypothesis stands after tonight in perihelion. The comet hypothesis has the most evidence. Natural volatiles, check. Asymmetric but explicable coma, check. Weak but non-zero non-gravitational acceleration, consistent with balanced jets or high mass, check. Size and composition uncertainties are narrowing but still favour large comet. The artifact hypothesis has fewer supports. No detected manoeuvres, no techno-signatures, no geometric structures, no radio emissions. The statistical rarity argument is disputed, and most of the claimed anomalies have plausible natural explanations. Loeb's score has already dropped from 6 to 4, and will likely drop further unless something shocking appears at perihelion. The debris field hypothesis is harder to score. It's plausible as an origin story for a weird comet, but without detected companions or stream signatures, it's indistinguishable from unusual comet ejected from a planetary system by normal processes. If a debris stream exists, we'll know by patterned arrivals and shared fingerprints. Here's a checklist for viewers to follow along over the next few years. Watch for new interstellar detections announced by the Minor Planet Center. Check the composition. If multiple ISOs show CO2-rich chemistry, that's a pattern. Check the velocity vectors. If several objects have similar speed and direction within uncertainties, that suggests a possible stream. Check arrival timing. If detections cluster within a few years rather than being evenly spaced, that's circumstantial evidence for a stream encounter. Also, watch for micrometeoroid data. Spacecraft like Parker Solar Probe, which flies close to the Sun, or missions in the outer solar system sometimes detect dust impacts. If there's a sudden increase in impacts with unusual composition or velocity, that could indicate passage through a debris field. No such alerts have been issued, but it's worth monitoring. Cultural impact. 3 interstellar visitors in 8 years have changed the conversation. Before Oumuamua, interstellar objects were theoretical curiosities. We knew they had to exist, but we'd never seen one. Now they're real. We've measured them, photographed them, analysed their chemistry. The sky feels more connected, more dynamic. We're not isolated. Objects from other star systems pass through our neighbourhood regularly. In a few decades, with better surveys, interstellar visitors might become routine. Oh, another ISO. Wonder where this one came from. That normalisation hasn't happened yet, but it's coming. Policy priorities are shifting too. Planetary defence agencies are starting to consider interstellar objects as a category, separate from near-Earth asteroids. The trajectories are different, the warning times are different, the mitigation strategies would be different. No immediate action is required because, as we've established, 3i Atlas is not a threat. But the conversation is happening. What if an ISO were on a collision course? How much? Warning would we get? Could we deflect it? These are questions that didn't need answers before 2017. End note on the Loeb scale. Keep it provisional. Tonight's number, whether it's 4 or 3 or 2, isn't destiny. It's a snapshot of our current uncertainty. As we get better data, the number should move. That's the point. Bayesian updating means you change your mind when evidence changes. Intellectual humility means admitting when you don't know, and being willing to say I was wrong when the data proves it. If 3i Atlas turns out to be a comet, Loeb was wrong to elevate its artifact probability as high as he did. But he was right to ask the question, and wrong to be mocked for asking. Science needs people willing to propose testable alternatives, even unpopular ones. The process corrects errors, but only if someone is brave enough or stubborn enough to make claims that can be tested. If 3i Atlas turns out to be something more than a comet, if perihelion reveals a maneuver, or if long-term tracking shows an anomaly, then Loeb was right to keep the door open. And the empiricists were wrong to close it prematurely. Science works either way, but it works better when the conversation stays honest and data-driven. Final image. Picture the night sky over Mars right now. Thin atmosphere, rust-coloured dust, and up there, visible to instruments if not the naked eye, a visitor from another star. A chunk of ice and rock, or maybe something stranger, blazing past at speeds that make our fastest rockets look like they're standing still. Instruments in orbit tracking it, beaming data back to Earth, where thousands of scientists and millions of curious humans are watching, wondering, hoping. Rosetta Stone or red herring? Comet or craft? Fragment of a lost world or just another rock in an infinite sky? We don't know yet. But we're looking, we're measuring, we're learning. And that's what makes tonight, October 3rd, 2025, more than just a flyby. It's a moment when our species, confined to one small planet, reaches out with its machines and its mathematics to touch something that came from the stars. The fourth visitor is out there somewhere, drifting through the dark. We'll meet it eventually. Maybe it'll be ordinary. Maybe it'll be extraordinary. But we'll be ready, telescopes trained, models refined, questions sharpened by what we learned from the first 3. The sky's no longer empty. It's alive with wanderers. And we, the temporary custodians of this pale blue dot, are finally learning to read the signs. Tonight we watch, tomorrow we wait. And somewhere in the data streaming back from Mars, maybe, just maybe, the universe is trying to tell us something new.